Imagine you are standing on a shore at night, looking out over an ocean that stretches beyond the horizon in every direction. You cannot see the other side. You cannot hear anything but the water. And you know, with absolute certainty, that this ocean contains 2 trillion islands. Not just barren rocks, islands with beaches, with mountains, with skies and seasons. Hundreds of billions of them in your local archipelago alone. Tens of billions of those islands sit in the gentle band where water stays liquid, where the temperature never swings toward freezing or boiling, where the chemistry of life could begin and hold. The ocean itself has existed for 13.8 billion years. The islands have been forming the whole time. Your own island appeared 4.5 billion years ago, and life emerged on it almost as soon as the surface cooled enough to hold liquid water, almost immediately. The implication is clear. If life could begin here that fast, under conditions that are not especially unusual, then it should have begun on countless other islands too. Given enough time, some of that life should have grown complex, intelligent, technological. Some of it should have built fires we could see. Some of it should have sent messages we could hear. The mathematics demands a crowded, chattering archipelago, a shoreline glowing with signal fires stretching from one end of the sky to the other. You look out over the water, it is black, it is silent, there is not a single light. And if tomorrow we find a fossilized bacterium in the rusty soil of Mars, that silence will become the worst news our species has ever received. Hello, and welcome to Sidereal. This is a channel about the universe, about black holes and neutron stars, about dark matter and the early cosmos, about the spacecraft we have launched, and the scientists who spent their lives asking questions the rest of us were afraid to ask. If you would like to support what we do, please subscribe and like this video. You can also leave a comment with your location and the time where you are listening. I read them. The question before us tonight is one of the oldest and most disturbing we have. The universe is vast beyond any scale. The human mind can truly inhabit. It contains more planets in the temperate zones of their stars than there are grains of sand on every beach on Earth. And yet, we hear nothing. No signals, no engineered structures, no evidence that anyone else has ever existed. Why is the universe so quiet, when every number we have says it should be shouting? By the time this video ends, you will understand the most serious explanations we have, and you will understand why some of them keep astrophysicists awake in the dark. We begin with the scale, because the scale is where the problem lives. It is not a metaphor, it is not a feeling. It is a set of numbers that refuse to add up. The observable universe, the portion we can see from our position on this small planet, contains something on the order of 2 trillion galaxies. That is not the whole universe, which may be infinite, but it is the part whose light has had time to reach us since the beginning. Each of those galaxies is an island city of stars. In a large spiral galaxy like our own, the Milky Way, the current best estimate is between 100 and 400 billion stars. Let us take 300 billion as a working number, knowing that it is uncertain by a factor of 2 in either direction. 300 billion suns. Some are too hot and short-lived to host complex life. Some are too cold and dim, but a significant fraction, perhaps 10 or 20%, are stars like our Sun, stable for billions of years, burning steadily in the main sequence, generous with their light and slow to change. That gives us tens of billions of sun-like stars in this galaxy alone. Around those stars, planets are the rule, not the exception. Before the Kepler Space Telescope, we did not know this. We suspected, we hoped, but we did not know. The first confirmed planet orbiting an ordinary sun-like star beyond our own was not found until 1995, when 2 Swiss astronomers, Michel Mayer and Didier Queloz, detected a strange world circling the star 51 Pegasi, a giant planet whipping around its star in just 4 days. It was so unexpected that they hesitated to believe their own data. 30 years later, the count of confirmed planets beyond our solar system has passed 5,000, and it climbs every month. Between 2009 and 2018, Kepler stared at a single patch of sky containing about 150,000 stars and measured the tiny dimming that occurs when a planet crosses the face of its star. What it found rewrote the textbooks. Planets are everywhere. The most recent analyses suggest that roughly 1 in every 5 Sun-like stars hosts a planet of roughly Earth's size orbiting in the habitable zone, the region where surface temperatures could allow liquid water to pool and persist. That is a conservative number. Some studies push it higher, but even at 1 in 5, the arithmetic becomes inescapable. In the Milky Way alone, there are billions of rocky planets where the temperature is not too hot and not too cold, where water can remain wet, where the basic solvent of life as we know it can do its work. Some of these worlds are close enough to name. Proxima Centauri, the nearest star to the Sun, 4.25 light-years away, has a planet of roughly Earth's mass orbiting in its temperate zone. A little further out, 40 light-years from here, a small red star called TRAPPIST-1 holds 7 rocky planets, 3 of them in the band where liquid water could survive. These are not statistical abstractions. They are specific places with specific masses and specific orbits that we have found within a stone's throw of our own doorstep. And if worlds like these cluster so thickly in our immediate neighborhood, the galaxy as a whole must hold them in numbers that stop meaning anything. Multiply the galaxies by the stars, and the stars by the planets. The number of potentially habitable worlds in the observable universe is not a number the human mind can hold. It is a number that belongs to astronomy, not to intuition. Try to picture it, and the picture dissolves. 10 billion trillion, a 1 followed by 22 zeros, at the low end. Every one of them a place where the sun rises, where rain might fall, where the chemistry that built you could, in principle, build something else. Try for a moment to actually hold one small corner of that number. Step outside on a clear, dark night, far from any city, and look up. On a good night, away from all light, the human eye can make out somewhere between 2,000 and 3,000 stars. That is the entire visible sky, everything our ancestors ever saw when they looked up in wonder and named the constellations and told their stories, 2,000 or 3,000 points of light. Now understand that every one of those stars sits within a few thousand light-years of you, a tiny bubble in one arm of one galaxy. The Milky Way holds 100 billion more that you cannot see, most of them hidden behind dust or simply too far and faint. And the Milky Way is one galaxy among 2 trillion. If you could somehow see, all at once, every star in the observable universe as a single grain of sand, you would be standing not on a beach but inside a desert that wraps around the entire Earth, kilometers deep, from pole to pole. And you have looked up and counted 3,000. That is the ratio between what a human being can perceive and what is actually there. It is not that the numbers are large. It is that they are large in a way the mind was never built to hold. And then there is time. The universe is 13.8 billion years old. Our planet formed 4.54 billion years ago. The first evidence for life on Earth, chemical signatures in ancient zircon crystals, fossilized microbial mats in rocks from Greenland and Australia, appears within a few 100 million years of the planet becoming habitable. 3.7 billion years ago, maybe earlier, Earth was already a living world. The moment the surface was cool enough and wet enough, life appeared. The moment the door opened, something walked through. If that happened here that fast, under conditions that are not rare in the galaxy, then life should have arisen on billions of other worlds too. It should have had billions of years of head starts. Earth is a relative latecomer to the universe. There are stars in this galaxy that are billions of years older than our Sun. Planets around those stars could have formed, cooled, and given rise to life while our solar system was still a cloud of diffuse gas. If intelligence emerged on even a tiny fraction of those worlds, and if it survived for any appreciable length of time, those civilizations would now be older than our entire evolutionary lineage, older than the primates, older than the mammals. They would have had time to do things we can barely imagine. The Copernican principle has been one of the most reliable guides in the history of science. It states, simply, that we are not special. The Earth is not the center of the solar system. The Sun is not the center of the galaxy. The Milky Way is not the center of the universe. Every time we have assumed a privileged position, the evidence has humbled us. Apply the Copernican principle to life, and you arrive at the confident expectation that we are mediocre, that life is common, that intelligence arises wherever conditions permit, that the universe should be full of voices. That is what the numbers say. That is what the logic demands. And yet, when we point our telescopes at the sky, when we turn our radio dishes toward the nearest stars, when we survey thousands of galaxies for the waste heat of civilizations that might have tamed the energy of entire suns, we find nothing. Not a single confirmed signal, not a single artificial structure, not a single photon that cannot be explained by natural processes. The Breakthrough Listen project, the most comprehensive search for extraterrestrial intelligence ever conducted, has surveyed thousands of stars and the plane of the galaxy using some of the most sensitive radio telescopes on Earth. It has found 0 unambiguous technosignatures. The search for Dyson spheres, hypothetical structures that an advanced civilization might build to capture the total energy output of its star, has turned up empty. The sky is natural. It is exactly what you would expect if we were the only ones here. This is the paradox. It is not a gentle mystery. It is a violent contradiction between two things that both appear to be true. The universe is built for life. The universe is silent. One of those statements must be wrong. And there is a detail that makes the silence sharper still. It is not just an absence of messages. It is an absence of presence. Quote, "A civilization only slightly more advanced than ours, using technologies we can already imagine, self-replicating probes, interstellar spacecraft, traveling at a fraction of light speed, could spread across the entire Milky Way in a span of time that is tiny compared to the age of the galaxy. 50 million years, maybe 100 million, a fraction of 1% of the time the galaxy has existed. If anyone had ever done it, we would see evidence. We would see probes in our solar system. We would see engineering on scales that nature cannot produce. We would not need them to send us a message. Their mere existence would be visible. We see none of that. The silence, then, is not merely an absence of deliberate communication. It is an absence of any detectable activity by any intelligence other than our own, across a canvas of billions of years and trillions of worlds. That is where the argument turns. You may have heard that finding life on another world, even a fossil, even a single cell, would be the greatest discovery in history. A confirmation that we are not alone, a second genesis in our own solar system. The scientific community would celebrate. The public would be transfixed. It would be the lead story on every news platform on Earth for weeks, and it would be a catastrophe. That sentence I placed at the beginning, if tomorrow we find a fossilized bacterium on Mars that will be the worst news our species has ever received, is not a rhetorical flourish. It is a logical conclusion from the Fermi paradox itself, one that we will reach together in the hours ahead. For now, I will leave it as an open wound, but the shape of the argument is this. If life arises easily, if it appears wherever liquid water and rock and time are present, then the silence becomes not just puzzling, but terrifying. The filter that stops intelligent civilizations from filling the galaxy cannot be behind us. It must be ahead. We must be walking toward it. That is the question that will follow us through this video. Not just why the universe is silent, but whether the silence is a warning. To understand what the silence might mean, we first have to understand exactly what we are measuring and what we are not. The contradiction between the expected abundance of life and the observed emptiness is not just a feeling. It can be written as an equation. In 1961, a young radio astronomer named Frank Drake gathered a small group of scientists at the Green Bank Observatory in West Virginia. The meeting was not meant to change the world. It was a quiet, speculative gathering, funded in part by the National Academy of Sciences, intended to assess whether searching for extraterrestrial intelligence was a legitimate scientific pursuit or a waste of telescope time. Drake had a particular reason to believe it was legitimate. The year before, in 1960, he had pointed the Green Bank radio dish at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for any signal that could not be natural. He called it Project Ozma, after the queen of the imaginary land of Oz. It was the first serious attempt in history to eavesdrop on the galaxy. He heard nothing but noise, with one heart-stopping exception, a strong signal that turned out to be a passing aircraft, but the experiment proved the search could be done at all. So when he called the meeting a year later, he needed an agenda. He needed a way to structure the conversation. So he wrote down, on a blackboard, a series of terms that, when multiplied together, would estimate the number of civilizations in the Milky Way with which we might communicate. The people in that room were an unusual collection. Carl Sagan was there, then a young astronomer in his mid-20s, near the start of a career that would make him the most recognizable scientist in the world. So was Melvin Calvin, a chemist who, partway through the meeting, received a telephone call informing him that he had just been awarded the Nobel Prize. There was Otto Struve, one of the most respected astronomers of his generation, and Bernard Oliver, an engineer from Hewlett-Packard, and a young neuroscientist named John Lilly, whose work on communication between humans and dolphins had captured the group's imagination. Half in earnest, half in jest, they began calling themselves the Order of the Dolphin, a small society of people willing to take seriously the possibility that we are not alone. It was a strange, brilliant, faintly ridiculous gathering, and out of it came one of the most durable ideas in modern science. Drake was not trying to produce a number, he was trying to organize what we did not know. The Drake equation has since become one of the most famous formulas in science. It is also one of the most misunderstood. It does not give an answer. It cannot. Several of its terms are completely unknown. What it gives is a framework for thinking about the problem, a way of separating the parts we can measure from the parts we can only guess. The equation multiplies 7 terms. The first is the average rate of star formation in the Milky Way, which we now know to be between 1 and 3 stars per year. The second is the fraction of those stars that have planets. Before 1995, this term was pure speculation. Today, thanks to Kepler and other planet-hunting missions, we know that fraction is close to 1. Nearly every star has planets. The third term is the average number of habitable planets per star, which Kepler has constrained to roughly 1 in 5 for Sun-like stars. As I have said, the fourth term is the fraction of those habitable planets on which life actually arises. The fifth is the fraction of those living worlds on which intelligence evolves. The sixth is the fraction of intelligent species that develop technology capable of interstellar communication. And the seventh, the final term, is L, the average lifetime of such a technological civilization, measured in years. The first 3 terms we can now fill in with real data. A star forms in the Milky Way somewhere between once and 3 times per year. Nearly every star has planets. Roughly 20% of Sun-like stars have an Earth-sized planet in the habitable zone. Multiplying these together gives us a number that is genuinely staggering. Even with conservative choices at every step, the Milky Way contains billions of rocky worlds where the temperature would allow liquid water to sit on the surface without boiling away or freezing solid. Billions of chances for life to begin. The next 2 terms, the fraction of habitable planets where life emerges, and the fraction of living worlds that produce intelligence, are currently blank. We have exactly 1 data point: Earth. Life appeared here within a few 100 million years of the planet becoming habitable, which suggests, but does not prove, that the origin of life might be relatively easy under the right conditions. But intelligence is a different question. Complex multicellular life took more than 3 billion years to appear after the first microbes. The evolutionary path from single cells to large, energy-hungry brains was not a straight line. It was contingent on a long series of accidents. The oxygen catastrophe, when photosynthesizing microbes flooded the atmosphere with a gas that was poison to almost everything then alive. The eukaryotic merger, the development of sexual reproduction, the Cambrian explosion, the colonization of land, the extinction events that cleared ecological space for new forms. We do not know how many of those steps are inevitable and how many are flukes. We do not know whether, if you rewound Earth's tape and played it again, anything like us would emerge. The 6th term, the fraction of intelligent species that develop technology we could detect, is also unknown, but we can say something about it. On Earth, only 1 lineage out of the billions that have ever existed crossed that threshold. The hominins. We achieved radio communication barely a century ago. Before that, a civilization in another star system could have pointed its most sensitive instruments at Earth for 4 billion years and heard nothing but the noise of wind and water. Which brings us to L, the final term, the average lifetime of a technological civilization. L is where the equation breaks open. If L is large, If civilizations typically survive for millions or billions of years after developing radio, then even if the preceding terms are small, the galaxy should be full of them. A single long-lived civilization would have time to spread across thousands of light years. Its signals would be detectable from across the galaxy. Its engineering would be visible to our telescopes. If L is small, if technological species tend to destroy themselves within a few centuries or millennia of inventing radio, then the galaxy could be a graveyard. Civilizations could blink on and off like fireflies in a storm, never overlapping in time, never lasting long enough to make contact. The Drake equation, for all its elegance, cannot tell us which of these possibilities is true. It cannot tell us whether the silence is a sign of absence or a sign of brevity. Sagan, who became the most famous champion of the search for extraterrestrial intelligence, used the equation to argue for optimism. He plugged in numbers that gave estimates of 1 million communicating civilizations in the Milky Way or more. Others, using equally plausible assumptions, arrived at 0. Michael Hart, in a paper published in 1975, argued that the absence of any evidence for extraterrestrial visitation of Earth over geological timescales implied that we are probably alone. The equation itself has no opinion. It is a mirror. For more, whatever you believe about the universe, you can find a set of numbers that will make the Drake equation say what you want it to say. This is not a failure of the equation. It is the point of it. Drake was not trying to produce a prediction. He was trying to organize ignorance. By breaking the problem into steps, he made it possible to ask which of those steps might be the one that silences the universe. It helps to make the two extremes concrete, because the gap between them is the whole drama. Take the first 6 terms and choose middle-of-the-road values for the ones we can estimate and generous values for the ones we cannot. You find that the Milky Way should be producing a new communicating civilization roughly once every few years to once every few centuries. Depending on how optimistic you are, that production rate barely matters on its own. What matters is how long each one lasts. If a civilization broadcasts for only 100 years before it falls silent, whether by self-destruction or by simply outgrowing radio, then at any given instant, the galaxy holds only a small handful of them, scattered across 100,000 light-years, almost certainly too far apart and too short-lived ever to notice one another. But if a civilization lasts 10 million years, then the galaxy fills up. The same production rate, multiplied by a lifetime 10,000 times longer, yields 10,000 times as many civilizations alive at once, a sky so crowded that contact would be not a hope, but a near certainty. So the entire question of whether we are surrounded by neighbors or utterly alone comes down to a single unknown number, and it is a number about which we have exactly one data point, ourselves, and our own value of it is still being written. We do not know if we will last another century or another million years, which means that when we plug ourselves into the Drake equation, we are not calculating an answer about the galaxy. We are placing a bet about our own future and calling it astronomy. And there is a subtlety here that is easy to miss. The Drake equation, as originally written, estimates the number of civilizations with which we might communicate at any given moment. That means it depends not just on how many civilizations have ever existed, but on how many exist right now, at the same time as us. If L is 1,000 years, and the galaxy produces one new civilization every 100,000 years, then at any given moment, there is roughly one civilization active per 100 civilizations that have ever lived. The odds of 2 existing simultaneously are poor. If L is 100 million years, then civilizations pile up. The galaxy fills with overlapping, communicating societies, a network of intelligence spanning tens of thousands of light years, visible from every direction. The silence we observe is consistent with either a very small number of civilizations or a very short L, or both. But what the silence is not consistent with is a large number of civilizations that survive for a long time. Those two things cannot both be true. The logic is iron. If the galaxy had produced even one civilization that survived for, say, 10 million years after developing interstellar technology, that civilization would have had time to colonize or at least visit every star system in the Milky Way. We would not need to search for their radio signals. We would find their artifacts in our own backyard. The Moon, the asteroids, the outer moons of Jupiter and Saturn, none of them show any sign of alien engineering. The silence is not a subtle statistical anomaly. It is a hard empirical boundary. So the question becomes, what sets L? What determines how long a technological civilization lasts? Is there something about the nature of intelligence, or the nature of technology, or the nature of the universe itself that places a hard limit on the lifespan of any species that reaches our stage? That is the question the Drake equation leaves us with. It is the question Fermi was circling around at that lunch table in 1950, without the benefit of a blackboard or a conference. It is the question that will occupy us for the rest of this video, because the answer, if it exists, is not just an astronomical curiosity, it is a statement about our own future. If L is short, then we are measuring ourselves. If the universe is silent because civilizations inevitably destroy themselves soon after they discover radio, then we are living inside the window right now. Our L is being written at this moment, in the decisions we make about nuclear weapons, about the climate, about the technologies we are building without fully understanding. The equation does not tell us what L is, but it tells us that L is the term that matters most. And it tells us that the silence is a number we are now, in our own small way, helping to determine. We do not yet know why the universe is quiet, but we know where to look for the explanation. It is in the gap between the first three terms of the Drake equation, which we can now fill with data, and the final four, which remain dark. Something in that darkness is doing the silencing. Something in that darkness is setting L. And if we ever find a fossil on Mars, we will know with terrible clarity which side of the equation contains the filter. In the summer of 1950, the town of Los Alamos, New Mexico, was still learning how to be something other than a secret. The Manhattan Project had ended 5 years earlier. The atomic bombs had been built and dropped. The scientists who had converged on this high desert mesa from universities across America and Europe were no longer working under wartime urgency. But the laboratory remained, and so did they. The Cold War was settling into its long, grinding rhythm. The hydrogen bomb was being designed in the same buildings where the first fission weapons had been assembled. The world had entered the nuclear age, and Los Alamos was still its center of gravity. Enrico Fermi was one of those who stayed. He had come to the United States from Italy in 1938, shortly after receiving the Nobel Prize in Physics for his work on nuclear reactions induced by slow neutrons. He had left fascist Italy with his Jewish wife Laura, using the trip to Stockholm as their escape route. By 1950, Fermi was 50 years old, a professor at the University of Chicago, and widely regarded as one of the greatest physicists alive, a man equally gifted at theory and experiment, capable of building a nuclear reactor beneath a football stadium and calculating the behavior of subatomic particles with a piece of chalk. He had a quality that colleagues described as almost unnerving, an ability to estimate the answer to any physical question within seconds, to within an order of magnitude, using nothing but logic and rough numbers. He called these Fermi problems, and he used them to teach his students how to think. How many piano tuners are there in Chicago? How far can a crow see on a clear day? You did not need to know the answer. You needed to know how to reason your way to within a factor of 10 of it. One day that summer, Fermi was walking to lunch with 3 colleagues. The Fuller Lodge, a large wooden building constructed in the 1920s as a dining hall for the Los Alamos Ranch School, served as the laboratory's cafeteria. The walk from the physics buildings to the lodge took perhaps 10 minutes, crossing the dry New Mexico ground beneath a sky that seemed to go on forever. The 4 men made this walk often. They talked about physics, about the laboratory, about the news, but on this particular day, the conversation drifted in an unexpected direction. The other 3 men were Edward Teller, Emil Konopinski, and Herbert York. Teller would later become known as the father of the hydrogen bomb, a brilliant and divisive figure whose testimony against Robert Oppenheimer during the security hearings of 1954 would permanently fracture his relationships with much of the physics community. Konopinski was a theoretical physicist who had worked on the design of nuclear weapons and would later become a prominent voice against above-ground nuclear testing. York, the youngest of the group at 28, had come to Los Alamos during the war as a graduate student and would go on to become the first director of the Lawrence Livermore National Laboratory, and later a dedicated advocate for arms control. They were not ordinary lunch companions. They were some of the sharpest minds of their generation, and they were walking to get something to eat. The conversation began with a cartoon. Several of the men had seen it in a recent issue of The New Yorker. The drawing showed a scene of flying saucers descending on a city, the kind of image that had become popular in the years since Kenneth Arnold reported seeing a formation of strange objects over Mount Rainier in 1947, the sighting that had introduced the phrase flying saucer into the American vocabulary. In the cartoon, the saucers were stealing something mundane. The caption made a joke about aliens taking public rubbish bins. This led to a discussion of flying saucers in general, and from there to the question of whether interstellar travel was actually possible, and from there to whether any civilization might have already achieved it. The men joked about it. The tone was light. They were scientists, and they were comfortable speculating about things that might be true. No one was taking the conversation too seriously. Then Fermi stopped walking. According to the accounts that were later pieced together, primarily through interviews conducted by the physicist Eric Jones in 1985, by which time York and Teller were among the few still alive to remember, Fermi went quiet for a moment. The others continued talking. Then Fermi spoke. "Where is everybody?" The question landed differently from everything that had come before. It was not a joke. It was not speculation. It was a challenge. The others understood immediately what he was asking. If the galaxy contains many civilizations more advanced than ours, and if interstellar travel is possible, then they should already be here. We should have seen them. We should have been visited, perhaps many times, perhaps continuously. The fact that we have not been visited, that we see no evidence of any extraterrestrial presence on Earth, in orbit, on the moon, anywhere, is itself a piece of data. And it is a piece of data that contradicts the assumption of a crowded galaxy. The conversation at the lunch table turned to this question, and Fermi began doing what he did best. He estimated. He started with the number of stars in the galaxy, the fraction likely to have planets, the fraction of those planets likely to be habitable. He assumed that life would arise on a reasonable fraction of habitable worlds, and that intelligence would arise on a reasonable fraction of living worlds. All of these numbers were unknown in 1950. We are still uncertain about some of them today, but Fermi was not trying to be precise. He was trying to test whether the basic logic held. What he found was that the logic collapsed under its own weight. Even with very conservative assumptions, the galaxy should have produced many civilizations long before Earth formed. Give one of those civilizations the ability to travel between stars, even at speeds well below the speed of light, and it would take only a few tens of millions of years to spread across the entire Milky Way. The galaxy is 100,000 light-years across. If a civilization could launch ships that traveled at 1% of the speed of light, a speed that is, in principle, achievable with technologies we can already imagine, it would cross that distance in 10 million years. Add some time for the civilization to establish colonies, for those colonies to grow, for new ships to be launched from the colonies rather than the homeworld, and the whole process of galactic colonization would still complete in 50 million years. Maybe 100 million. That sounds like a long time by human standards, but the galaxy is more than 13 billion years old. 50 million years is less than 0.5% of the galaxy's age. It is a rounding error. If a single civilization had ever launched an expansion wave, it would have filled the entire galaxy long before the Earth existed. So where are they? Where are the probes, the colonies, the artifacts, the signals? Where is the evidence that any of this ever happened? The galaxy should be saturated with intelligent activity. We should be tripping over alien archaeology in every direction. Instead, we see nothing. The sky is natural. The solar system is empty of any trace of engineering. We have found no alien probes, no alien machinery, no alien monuments on the moon. The logic was so stark that Fermi did not need a blackboard. He could see the contradiction in his head. A crowded galaxy and an empty sky cannot both be true. Teller later recalled that the conversation moved on, but the question stayed with him. It stayed with all of them. It was one of those questions that, once asked, cannot be unheard. The Fermi paradox, though it would not be given that name for another 2 decades, was born in those few minutes on a walk to lunch in the New Mexico desert. A question asked in passing, almost as an aside, that has haunted astronomy ever since. The term Fermi paradox itself was not widely used until the late 1970s. Michael Hart, in his 1975 paper titled an explanation for the absence of extraterrestrials on Earth, formalized the argument without naming it after Fermi. Hart's paper was blunt. He reviewed the evidence for and against the existence of extraterrestrial civilizations and concluded that the only reasonable explanation for the absence of visitation was that no such civilizations exist. We are alone, he argued, not just in the solar system but in the galaxy, and possibly in the observable universe. The paper provoked a strong response. Many astronomers found its conclusion premature, even arrogant, but the logic was difficult to refute. Hart had simply taken Fermi's lunchtime calculation and written it down as a formal argument. The physicist David Viewing, writing in the mid-1970s, independently arrived at similar conclusions. So did Frank Tipler, who argued in 1980 that the absence of extraterrestrial artifacts on Earth is, by itself, sufficient to rule out the existence of any technological civilization in our past light cone, the region of the universe from which light has had time to reach us. Tipler's argument was even stronger than Hart's. He claimed that if a single civilization had ever existed in the history of the galaxy, its self-replicating probes would already be here. The fact that they are not means that we are the first. These were not fringe voices. They were respected physicists making arguments from first principles. And they were taken seriously. The Fermi paradox had matured from a lunchtime question into a genuine scientific problem, one that sits uncomfortably at the intersection of astronomy, biology, and philosophy. It is worth noting that not everyone accepted the leap from an empty sky to an empty galaxy. In 1983, Carl Sagan and William Neumann published a careful rebuttal, sometimes called the response of the soliloquy, arguing that the colonization calculations were too quick. Real populations, they pointed out, do not expand forever at their maximum possible rate. They slow, they stabilize, they choose not to grow. A civilization might spread for a while and then stop, content with a handful of worlds, in no hurry to pave the galaxy. If expansion is slower and more reluctant than the simple exponential models assume, then the galaxy could take far longer to fill, perhaps longer than it has yet existed, and the fact that we see no one would carry much less weight. The debate was never fully settled. It could not be, because it turns on how a typical civilization behaves, and we have never observed a typical civilization. We have observed exactly one, and it has not yet decided what it is going to do. But the exchange marked the paradox as a serious scientific dispute, rather than a piece of lunchtime whimsy, with careful people on both sides, arguing from the same silence toward opposite conclusions. But the paradox is not just about whether extraterrestrials exist. It is about what the absence of evidence tells us about the nature of intelligence itself. Fermi's question, "Where is everybody?" is deceptively simple. Answering it requires us to confront possibilities that are, in their own way, more disturbing than the existence of aliens would be. Because the calculation that Fermi performed in his head, the calculation that Hart and Tipler later formalized, does not just say that the galaxy should be full of life. It says that the galaxy should be full of life that has had billions of years to develop, to expand, to leave its mark on every star and every planet. The fact that we see no trace of any of this implies that something, somewhere, is preventing it. Something stops intelligent life from filling the galaxy. Something imposes silence. And the question that follows from that, the question that has kept the Fermi paradox alive and urgent for more than 70 years, is whether that something lies behind us, in the deep history of life on Earth, or ahead of us, waiting in our future. The logic that Fermi sketched on that walk in 1950 is even more forceful than most people realize. We tend to think of interstellar travel as something that would take many thousands of years to go from star to star, something so slow and difficult that it might never be practical. That is true if you are thinking about a single mission, a single ship, a single crew making the journey. But civilizations do not have to travel that way. They do not have to send living beings across the void. They can send machines. The concept is called a von Neumann probe, named after the Hungarian-American mathematician John von Neumann, who, in the 1940s and 50s, developed the theoretical framework for self-replicating automata, machines capable of building copies of themselves given raw materials and energy. A von Neumann probe is a spacecraft designed to travel to a star system, land on an asteroid or a moon, mine the necessary materials, and construct several copies of itself. Those copies then launch toward other star systems, and the process repeats. Each probe is a seed. The seeds multiply. Picture yourself as one of those machines. You arrive in an unknown star system after a journey of decades, and you fall silently toward a small metal-rich asteroid. You have no crew. You do not sleep, because you are never awake in the way a person is awake. You anchor to the surface. You begin to dismantle the rock around you, atom by atom, sorting iron from nickel from carbon, and you build. Not one copy of yourself, 2, 3. When they are finished, they light their engines and fall away into the dark, aimed at stars you will never see. And you power down, your task complete. You are patient in a way no living thing could ever be. You have all the time in the universe, because you are the kind of thing that turns time into distance. The mathematics of exponential growth are implacable. If a single probe arrives at a star system and builds just 2 copies of itself, and those 2 copies each build 2 more, the number of probes doubles with each generation. 10 generations produce roughly 1,000 probes. 20 generations produce 1,000,000. 30 generations produce 1,000,000,000. The Milky Way contains somewhere between 100 and 400 billion stars. How many generations would it take to place a probe in every star system? About 40. 40 doublings. Hins, each taking however long the interstellar journey requires, and the entire galaxy is visited. Now consider the timescale. At 10% of the speed of light, a velocity that is demanding but not physically impossible, a velocity that a sufficiently advanced civilization could achieve using technologies like nuclear pulse propulsion or laser-driven light sails, a probe would travel from one star to the next in a few decades. Add a few decades for the probe to land, mine, and build its copies. Each generation takes perhaps a century. 40 generations take 4,000 years. Even if the probes travel at only 1% of light speed, and each generation takes 1,000 years. 40 generations take 40,000 years. The galaxy is 100,000 light-years across, so at 1% of light speed, a wave of probes would take 10 million years to cross it if they all launched from one side. But probes are not launched from one side, they spread in all directions from their point of origin. A single civilization launching a wave of self-replicating probes from a single star could saturate the entire Milky Way in something between 10 million and 100 million years. 100 million years. The galaxy is more than 13 billion years old. 100 million years is less than 1% of its age. It is a sliver of cosmic time. It is less than the time that separates us from the early Cretaceous period, when flowering plants first appeared and dinosaurs walked through forests of ferns. The Earth was here then, life was here, complex life was here, and the galaxy was already ancient. Any one of the billions of sun-like stars that predate our sun by a few billion years could have been the home of a civilization that launched probes in the early morning of the galaxy's history. Those probes would have had time to cross the Milky Way 100 times over. They would have had time to visit every star, map every planet, and leave behind machines that we would find today, still functioning or not, but unmistakably artificial. And this deepens the silence into something harder. It is not just that the galaxy is quiet, it is that the galaxy appears never to have been disturbed by any expansion event at all, across billions of years, despite the fact that a single such event, launched by a single civilization, would have filled every corner of it long before our solar system formed. The silence is not just an absence of radio messages. It is an absence of any physical trace of any technological species that has ever existed anywhere in the Milky Way. We have searched the Moon, the asteroids, the planets, the moons of the outer solar system. We have looked at the surfaces of Mars and Mercury and the icy crust of Europa. We have mapped the sky at radio wavelengths and optical wavelengths and infrared wavelengths. We have found nothing that requires an artificial explanation. Not a single artifact. Not a single unexplained structure. Not a single piece of debris that could not have come from a natural process or from our own spacecraft. Michael Hart's paper in 1975 made this point with force. He argued that if extraterrestrial civilizations existed, some of them would certainly have developed interstellar travel, and some of those would certainly have attempted to colonize other star systems. Given the timescales involved, the entire galaxy would have been colonized many times over. The fact that Earth has not been colonized and shows no evidence of ever having been visited implies that no such civilizations exist. The conclusion was stark. Hart was not arguing that extraterrestrial intelligence is rare. He was arguing that it does not exist at all, anywhere in the Milky Way, and possibly anywhere in the observable universe. Frank Tipler, writing 5 years later, sharpened the argument further. He pointed out that a von Neumann probe, once launched, would be effectively permanent. I think, even if the civilization that built it died out, the probes themselves would continue to replicate as long as they had access to raw materials. They would become a permanent feature of the galaxy, as durable and as widespread as the stars themselves. The fact that we do not see any such probes anywhere means that they were never launched. And the fact that they were never launched means that no civilization has ever existed that was both willing and able to build them. Tipler's conclusion was even stronger than Hart's. He claimed that the absence of extraterrestrial artifacts is sufficient to rule out the existence of any technological civilization in our entire past light cone, the volume of the universe from which light has had time to reach us since the Big Bang. These arguments are powerful because they close off a common escape route. Many people, when confronted with the silence, suggest that perhaps extraterrestrial civilizations are simply not interested in colonization. Perhaps they prefer to stay home. Perhaps they have transcended the physical universe and moved into some other realm of existence. Perhaps they are too advanced to bother with crude technologies like radio. Hart and Tipler's response to these suggestions is simple. It only takes one, out of the millions or billions of civilizations that the statistics demand, only one needs to behave differently. Only one needs to be expansionist, or curious, or paranoid, or simply interested in ensuring its own long-term survival by spreading to other stars. If a single civilization in the history of the galaxy ever launched a wave of self-replicating probes, those probes would still be here. They would be everywhere. The fact that they are nowhere implies that no civilization, not one, in the entire history of the Milky Way has ever taken that step. And this is where the concept of the Dyson sphere enters the picture. In 1960, the physicist Freeman Dyson proposed that a sufficiently advanced civilization would eventually seek to capture the total energy output of its star. It would build a shell, or a swarm, of solar collectors surrounding the star completely, absorbing every photon and radiating waste heat into space. A Dyson sphere would be detectable across interstellar distances. It would glow brightly in the infrared, a star that had been wrapped in engineering. Searches for such megastructures, for partial swarms, or for any construction that would alter a star's natural light, have been conducted for decades. The Glimpsing Heat from Alien Technologies Survey, along with other programs, has examined millions of galaxies for the infrared signatures of star-spanning civilizations. It has found natural explanations for every unusual signal. There are galaxies that glow brightly in the infrared, but all of them can be explained by dust, by star formation, by the ordinary processes of galactic ecology. Not one demands the presence of engineering. Tabby's star, listed in the catalogues under a long identifying number, provided a moment of genuine excitement in 2015. The star, observed by the Kepler Space Telescope, showed irregular dimming that could not easily be explained by a transiting planet. The dips in brightness were deep, sometimes swallowing more than a fifth of the star's light, and they occurred at irregular intervals. No natural explanation was immediately obvious. The astronomer Tabetha Boyajian, who led the study and gave the star its nickname, carefully laid out the possibilities. A. Including the speculative suggestion that the dimming could be caused by an alien megastructure, a partial swarm of collectors under construction. The media seized on the story. For a few months, the world wondered whether we had finally found evidence of extraterrestrial engineering. But follow-up observations showed that the dimming was wavelength dependent. Different colours of light were blocked by different amounts, which is exactly what you would expect if the star were being occulted by dust, not solid structures. The evidence now strongly favours a natural explanation, probably an uneven ring of dust or a swarm of cometary fragments. Tabby's star is fascinating, but it is not a technosignature. 5. And so the galaxy remains empty of visible engineering. No Dyson spheres, no self-replicating probes, No interstellar empires detectable across the void. The silence is complete. This is the point at which the Fermi paradox ceases to be a gentle puzzle. The universe is not merely quiet in the sense that no one is sending us messages. It is quiet in the sense that no one appears to have done anything at all, anywhere, that we can see. The canvas is blank, and the blankness itself is a piece of information. What kind of information? That is where the disagreement begins. Hart and Tipler concluded that the blankness means absence. No one exists. No one ever has. We are the first, or we are alone. Other scientists have drawn different conclusions. Perhaps the probes are here, and we have not recognized them. Perhaps they are too small, or too well disguised, or operating on principles we do not understand. Perhaps they are waiting. Perhaps they have a reason for staying hidden that we cannot guess. But the problem with all of these suggestions is the same problem that faced Fermi at that lunch table. It only takes one. If 1 million civilizations have existed in the history of the galaxy, and nearly all of them chose to stay home, or hide, or transcend, or keep silent, and one chose to expand, that one would be visible, that one would have left marks. The fact that no marks exist tells us that the fraction of civilizations that expand is, for some reason, 0. Why would it be 0? What prevents every single civilization from taking that step? What imposes silence on every species that reaches the threshold of technology? That is the question that leads, inevitably, to the darkest possibility, the possibility that something kills them, something that operates so reliably that not a single civilization in billions of years has ever escaped it. Something waiting ahead of us. In 1964, a Soviet astronomer named Nikolai Kardashev was thinking about how you would even recognize an advanced civilization if you saw one, and he proposed a way of ranking them that had nothing to do with their art or their politics or their biology. He ranked them by energy. A civilization, Kardashev reasoned, is a thing that captures and uses energy, and the more advanced it becomes, the more energy it commands. So he sorted them into types. A Type 1 civilization harnesses all the energy available on its home planet, every scrap of sunlight that falls on it, every current of wind and water, the heat of its own interior. A Type 2 civilization has outgrown a single planet and captures the entire output of its star, the whole furnace, perhaps with a shell of collectors of the kind Freeman Dyson imagined. A Type 3 civilization has spread across an entire galaxy and draws on the combined energy of hundreds of billions of stars. By this measure, we are not even a Type 1. We are somewhere around Type 0.7, a species that still runs mostly on the buried remains of ancient sunlight and has not yet learned to capture even the full daily budget of light its own planet receives. Kardashev's scale is a ladder, and we are on the lowest rungs, looking up. But the scale is useful for the paradox in a specific way. It tells us what to look for. A Type 2 or Type 3 civilization would not be subtle. A civilization wrapping a star, or many stars, in energy-collecting structures would leave a signature we could detect across enormous distances because the laws of thermodynamics are strict. Energy captured and used does not vanish. It is degraded, turned into waste heat, and radiated back out into space as infrared. The same dull glow a warm engine gives off, the same heat you feel from a lamp that has been on too long. A star being fully exploited by a Type 2 civilization would dim in visible light and blaze in the infrared. A galaxy colonized by a Type 3 civilization would show the same fingerprint written across all its stars at once, unusually dark in visible light, unusually bright in the infrared, an entire galaxy quietly humming with the waste heat of industry. This is not a thought experiment. It is a survey that has actually been carried out. Using an orbiting infrared telescope that mapped the whole sky, a team of astronomers examined roughly 100,000 galaxies, looking specifically for that fingerprint. Galaxies too bright in the infrared to be explained by ordinary starlight, as if their stars were being harvested wholesale. If even a small fraction of galaxies hosted a spreading Type 3 civilization, some of them should have lit up in the data. The result, published in 2015, was clean and disappointing. A handful of galaxies showed slightly unusual infrared signatures, but every one of them could be explained by natural processes, by dust, by bursts of star formation, by the ordinary metabolism of a galaxy. Not one demanded, or even clearly suggested, a civilization. Across 100,000 galaxies, containing on the order of 10,000 trillion stars, there was no sign that anyone had ever climbed to the top of Kardashev's ladder. Think about what that search actually ruled out. It was not looking for a faint radio whisper from a single star. It was looking for civilizations so vast that they had rearranged the light of entire galaxies, and it looked at 100,000 of them and found nothing. This is the silence at its largest scale. Not just our galaxy, but 100,000 others, all apparently untouched, all shining with the plain, unmodified light of stars that no one has ever put to work. And the searches closer to home have come up just as empty. The Breakthrough Listen program, funded to be the most sensitive and systematic hunt for radio and optical signals ever mounted, has swept over 1 million nearby stars, the entire plane of our galaxy, and 100 nearby galaxies. It has recorded a small number of tantalizing signals, brief, narrow, artificial-looking spikes that made hearts race in the control room, and every single one, on examination, has turned out to be interference from our own technology, a satellite or a phone or a stray transmitter here on Earth. One promising candidate, detected in the direction of Proxima Centauri, held up for months of analysis before it too was traced back to human equipment. Every apparent voice from the dark has turned out to be an echo of ourselves. So the empirical picture is not one of a search that has barely begun. It is one of a search that has already looked, hard and widely, across radio and infrared and optical light, from single nearby stars out to distant galaxies, and has consistently found a sky that behaves exactly as it would if there were no one out there at all. The silence is not a gap in our data. It is, increasingly, the data. If expansion across the galaxy is as inevitable as the physics suggests, and if the galaxy shows no trace of any such expansion across billions of years, then something must be preventing it. Something must intervene between the emergence of intelligence and the colonization of the stars. Something must turn every technological civilization into silence before it can leave a mark. In 1996, an economist and polymath named Robin Hanson published a short essay that gave this something a name. Hanson was not an astronomer. He was a researcher at George Mason University, a man with degrees in physics and philosophy who worked at the intersection of economics, artificial intelligence, and the deep future. He had trained himself to think about very long timescales and very large numbers, and he had been turning the Fermi paradox over in his mind. The essay he produced was titled, "With Characteristic Directness, The Great Filter, Are We Almost Past It?" And the argument it contained has quietly shaped how a generation of scientists thinks about our place in the universe. The idea is this: for a civilization to become visible across interstellar distances, for it to leave traces that we could detect, a long chain of things has to happen in sequence. It begins with the right star system, a star that is stable and long-lived, located in a region of the galaxy, where heavy elements are abundant enough to form rocky planets, but where radiation from supernovae and the galactic core is not so intense that it sterilizes everything. The chain continues with the formation of a habitable planet, one with liquid water and a magnetic field and a stable climate. Then comes the origin of life itself, the leap from non-living chemistry to self-replicating molecules, to cells, to metabolism. Then the emergence of complex cells with a nucleus. Then multicellular organisms, the kind that can build structures and process information. Then the evolution of a large brain, tool use, language, abstract thought. Then the development of science and technology, the kind that can build radio transmitters and spacecraft. And finally, the step that determines everything else, the expansion into the galaxy, the establishment of colonies around other stars, the construction of a civilization so widespread that it could not possibly be missed. Hanson's insight was that at least one of these steps must be extraordinarily improbable, not merely difficult. Improbable to the point of near impossibility, because the silence we observe is not a mild statistical fluctuation. It is not a matter of civilizations being slightly rarer than we expected. The silence is total. It demands that the product of all these probabilities, multiplied together, be close to zero. And the only way for a product to be close to zero is for at least one of the terms in it to be close to zero. Somewhere in that chain of steps, there is a gate so narrow that almost nothing gets through. That gate is the Great Filter. It is worth pausing on how strange the shape of Earth's own history is, because it contains a clue about where such a gate might sit. Life appeared here almost the instant the planet could support it, which hints that the very first step, the origin of a living cell, might be easy. But then something odd happened. For nearly 2 billion years after that, life did almost nothing. It stayed as simple single cells, dividing and surviving but never becoming anything more. 2 billion years is close to half the age of the Earth, an ocean of time in which life had every opportunity to become complex and simply did not. Then, once, as far as we can tell, exactly once, 2 microbes merged into a single, more complicated cell, the ancestor of every plant and animal and fungus that has ever lived. Some biologists look at that long delay and that apparent one-time event and suspect the gate is right there, not in the birth of life, but in the leap from simple life to complex life. If that is the hard step, it is behind us, and it may explain the silence all by itself. Others point elsewhere. Perhaps the gate is intelligence itself. The fact that in 4 billion years of life on Earth, with countless species and countless nervous systems, only one lineage ever built a radio. Perhaps it is technological civilization, which our own species reached only in the last flicker of an eyelash. Perhaps it is the survival of that civilization across the long ages needed to reach the stars. The honest answer is that we cannot yet say which step, or steps, are the improbable ones. There may even be several hard steps rather than one, which would make advanced life rarer still. What we can say is that the total must be small enough to explain a completely silent sky, and that every step we can confidently place behind us makes the remaining possibilities more constrained and the question of the future more urgent. Now hold that idea next to a second one, and you will see why Hanson's essay carries a chill that outlasts a first reading. The Great Filter is somewhere in the chain. But where? Is it a step we have already taken, or a step we have not yet reached? The steps divide cleanly into 2 groups. There are the steps behind us, the ones our own history has already passed through, the formation of a good star, a habitable planet, the origin of life, the complex cell, multicellularity, intelligence, technology. We are living proof that all of these can happen, because all of them happened here. And then there are the steps ahead of us, the establishment of a sustainable, long-lived, spacefaring civilization that survives for millions of years and spreads beyond its home world. If the Great Filter lies behind us, if one of the steps we have already passed is the one that almost never happens, then we are through the bottleneck. We are rare, perhaps unique, but we are safe. The hard part is done. The galaxy is empty because life like ours almost never gets this far, and we are the freakish exception, the one throw of the dice that came up right. The future is open. But if the Great Filter lies ahead of us, if the nearly impossible step is one we have not yet reached, then the news is very different. Then we are not special at all. We are typical. We have done all the easy things, the things that countless other species also managed, and we are now approaching the same wall that stopped every one of them. The silence of the galaxy would not be a sign of our good fortune. It would be a preview of our fate. And the typical outcome for a species standing where we stand would be to fail, to fall silent, to join the long line of civilizations that came this far and no further. That is the fork. Behind or ahead, the past or the future. A universe where we are the improbable first, or a universe where everyone comes this far and then dies. And here is the part that turns an abstract argument into something personal. The 2 positions make opposite predictions about what we should hope to find when we go looking for life elsewhere. Most people assume that discovering alien life would be good news, a companionship, a reassurance, a sign that the universe is fertile and we are part of something larger. Hanson's framework inverts that assumption completely, because the more places we find life, the more of the early steps we prove to be easy, and the more of the filter we push into the future, where it is waiting for us. This is the argument that the philosopher Nick Bostrom of the University of Oxford laid out in an essay published in 2008 under a title that says everything. Where are they? Why I hope the search for extraterrestrial life finds nothing. Bostrom is not a pessimist by temperament. He is a careful reasoner who spends his life thinking about the risks that could end human civilization. And his conclusion was that every discovery of extraterrestrial life should make us more worried, not less. A dead galaxy is the galaxy we should be praying for. An empty Mars, a sterile Europa, a lifeless sky, these would be the most reassuring findings imaginable, because they would suggest that the filter lies safely behind us, in some early step that other worlds rarely manage. The discovery of life, especially complex life, especially independent life, would suggest the opposite. It would suggest that the filter is still to come. To see why, follow the logic one step at a time, because it does not bend. Suppose we search Mars and find nothing. No fossils, no microbes, no chemical trace of anything that ever lived. That silence, disappointing as it would feel, is compatible with the filter being the origin of life itself. The possibility that going from dead chemistry to a living, replicating cell is the near impossible step, a fluke so rare that it may have happened only once in our entire galaxy. If that is the filter, then it is behind us. We are through. We can breathe. But suppose instead we find life on Mars, and suppose it turns out to have arisen independently of Earth, a genuinely separate origin, a second sample of biology that owes nothing to our own. Then the origin of life cannot be the rare step, because it happened twice in one small solar system, around one ordinary star. And if it happened twice here, it must have happened countless times across the galaxy. The universe must be soaked in life, which means the filter that keeps the sky silent cannot be the origin of life. It has to be something later in the chain, and every step later in the chain is a step that we too must pass. The filter moves from behind us to in front of us. The silence stops being a reassurance and becomes a sentence. Hanson understood this in 1996, and Bostrom made it explicit 12 years later, and it is the reason a certain kind of scientist feels a private flinch every time a headline announces the possible detection of life beyond Earth. They are not being ungenerous. They are doing the arithmetic. The more common life turns out to be, the more certain it becomes that something, somewhere in the steps ahead of us, reliably ends civilizations before they can fill the sky. The great filter does not tell us what that something is. It only tells us that it exists, and that its location, behind us or ahead of us, is the single most important unknown about the human future. Everything else we might learn about the cosmos is a footnote next to that one question. And the strange, uncomfortable truth is that we may be about to answer it. Not through philosophy, through a rover, and a drill, and a handful of Martian rock, which is where we go next. The search for life on Mars has been one of the central projects of planetary science for more than half a century, and it has already produced one false dawn that is worth remembering, because it shows how heavy this question is even when the answer turns out to be no. In 1984, a meteorite was found on the ice of Antarctica in a region called the Allen Hills. It was a piece of Mars, one of a small number of rocks that were blasted off the Martian surface by an ancient impact, drifted through space for millions of years, and eventually fell to Earth. It sat in a collection drawer for years before anyone examined it closely. Then, in 1996, a team of scientists led by David McKay at the Johnson Space Center published a paper claiming that the rock contained possible evidence of past Martian life, microscopic structures that resembled fossilized bacteria, along with certain minerals and organic molecules that, on Earth, are often associated with biology. The announcement was so significant that the President of the United States, Bill Clinton, walked out onto the south lawn of the White House to address it directly. If confirmed, he said, it would be one of the most stunning insights into the universe that science had ever uncovered. It was not confirmed. Over the following years, the scientific community examined the claims and found that every feature the team had pointed to could be explained without invoking life. The tiny structures were probably too small to be cells. The minerals could form through ordinary chemistry. The organic molecules could have seeped in from Earth or formed without biology. The consensus today is that the meteorite, known by its catalogue name as a specimen from the Allen Hills, does not contain proof of Martian life. But the episode left a mark. It showed how close the question sits to the surface of our civilization, how quickly a rock in a drawer can become a presidential address, and how badly we want the answer to be yes. Since then, the search has become methodical. The Viking landers, which touched down in 1976, had already carried experiments designed to detect microbial metabolism in the Martian soil. The results were ambiguous. One experiment produced a positive signal that most scientists now attribute to reactive chemistry in the soil rather than biology. But the ambiguity has never been fully resolved, and one of the original investigators argued to the end of his life that Viking had found life, and we had failed to believe it. More recent missions, the Curiosity rover, the Perseverance rover, have focused on characterizing the ancient Martian environment, searching for organic molecules and identifying places where life might once have lived. Curiosity, exploring an ancient lake bed in Gale Crater, has confirmed that Mars once had standing water, the right chemistry, and the energy sources that life on Earth depends on. It has also detected methane in the Martian air, a gas that, on Earth, is produced mostly by living things, though it can also be made by ordinary geology. The methane rises and falls with the Martian seasons in a pattern no one has fully explained. And to complicate matters further, a European spacecraft built specifically to hunt for it from orbit has struggled to detect the methane that the rover reports from the ground. The puzzle is unresolved. It may be biology, it may be chemistry, we do not yet know. Perseverance, meanwhile, is doing something no mission has done before. It is exploring Jezero Crater, the site of an ancient river delta where water once flowed into a lake, and it is collecting samples of rock and sealing them into sterile tubes, leaving them on the surface for a future mission to retrieve and carry home. The plan to bring those samples back to Earth is one of the most ambitious undertakings in the history of space exploration, and its timeline and cost are under constant review. But if it succeeds, then for the first time, pieces of Mars chosen for their scientific promise will be examined in the finest laboratories on Earth, with instruments far too large and delicate to send to another planet. The samples are sitting on Mars right now, waiting. The search is careful, patient, and driven by one of the deepest questions a human being can ask. Are we alone? Stand for a moment on the Martian surface as it was 3.5 billion years ago, before you assume the answer is no. The sky is pink rather than black, thick enough to hold weather. A river runs past you across a plain of red rock, carrying sediment down into a lake that stretches to the horizon. It is cold, but not impossibly cold. There is liquid water, and there is chemistry, and there is time. At this same moment, 90 million kilometers away, the young Earth is doing the same thing. And on Earth, in warm water not so different from this, life is already stirring. Two worlds, side by side, around the same star, both wet, both warm enough, both stocked with the same raw ingredients. On one of them, something crossed the line from chemistry to life. The question that will decide a great deal about our future is whether it also happened on the other. Because if it did, if we find life on Mars, and if that life turns out to have started on its own, then we have learned something about the probability that dead matter becomes living matter. We will have learned that on two planets in the same solar system, both within the temperate zone of the same star, life emerged. Two worlds, two beginnings, in a single planetary system. If life arose twice around one star, then the origin of life cannot be the improbable step. It must be something that happens wherever conditions permit. The galaxy, which contains billions of temperate zone planets, must therefore be teeming with simple life. The fourth term of the Drake equation, the fraction of habitable planets where life emerges, would be close to 1. And if that term is close to 1, then the great filter cannot be behind us. It cannot be the origin of life. 201sts. It cannot be the emergence of the complex cell or of multicellular bodies, because if the galaxy is soaked in life, then some fraction of those living worlds will inevitably climb the same ladder we climbed, and some fraction of those will inevitably produce minds. The numbers are simply too large for it to be otherwise. Even if intelligence is a 1 in a million outcome, 1 billion life-bearing planets still produce 1,000 thinking species, 1,000 civilizations in the Milky Way, and we would be back at Fermi's question, standing at the lunch table in the desert. Where are they? The silence tells us they are not here. And if the origin of life is easy, if Mars proves that life appears wherever water and rock and time are present, then the reason they are not here cannot be that they never existed. It must be that they never survived. In that case, the great filter lies ahead of us. Every intelligent species that ever emerged in the Milky Way would have run into it. Every single one would have failed to pass through. The silence would not be an absence. It would be a graveyard, and we would be walking toward the same grave. This is why a fossilized bacterium on Mars would be such grim news. Not because a fossil is dangerous, but because of what it would imply. It would not be a discovery that fills us with wonder so much as a discovery that narrows our future. The same reasoning that makes us expect life to be common, once we find a second genesis, also makes us expect that the step from intelligence to long-term survival is one that almost nobody survives. There is one escape hatch, and it is worth naming carefully, because it is the hinge on which the whole argument turns. The dread only follows if the Martian life arose independently. Earth and Mars have been trading rocks for billions of years. The very meteorite found in Antarctica is proof that material crosses between the two worlds. It is entirely possible that life began on one planet and was carried to the other inside a rock, a process called panspermia. If Martian life turned out to share the same biochemistry as Earth life, the same genetic code, the same molecular handedness, then it might not be a second genesis at all. It might be a cousin, seeded from the same source. And in that case, the argument softens, because we would still have only one true origin of life, not two. This is why, if life is ever found on Mars, the first and most urgent question will not be whether it is alive, but whether it is related to us. A relative would be a wonder, a stranger would be a warning, and Mars is not the only place the question is being asked. Further out in the solar system, two small icy moons have quietly become some of the most promising places to look for life beyond Earth, and they matter here for a precise reason. Europa, a moon of Jupiter, and Enceladus, a much smaller moon of Saturn, both hide oceans of liquid water beneath their frozen crusts, oceans kept warm not by sunlight, which barely reaches them, but by the flexing and squeezing of tides as they orbit their giant planets. Enceladus vents plumes of that ocean water directly into space through cracks near its south pole, and a passing spacecraft has already flown through those plumes and tasted them, finding salts and organic molecules and hints of the kind of chemistry that on Earth feeds life at the volcanic vents of the deep sea. Europa's ocean may hold more than twice as much water as all the oceans of Earth combined, sealed beneath a shell of ice, dark and undisturbed for billions of years. These worlds sharpen the same blade. If life is found in the ocean of Europa, or in the spray of Enceladus, and if it turns out to have begun independently, then we would have not two, but 3 or 4 separate origins of life around a single star. And the more origins we count, the harder it becomes to believe that the beginning is difficult, and the more forcefully the filter is pushed into the future, into the space ahead of us. Each new place we find life, if that life is truly its own, is another turn of the screw. This is the strange position we have argued ourselves into. The most thrilling discovery our species could make, life elsewhere, life nearby, life we could study, is also the discovery that a certain kind of careful thinker most quietly dreads. The astrobiology community does not tend to talk about this in press releases. The papers announcing the discovery of Martian biosignatures, if that day comes, will not include a paragraph about what the discovery implies for human extinction. But the implication is there, unspoken, in the numbers, and every careful astrobiologist knows it. The more easily life arises, the more likely it becomes that something reliably ends it. The more common the spark, the more meaningful the silence. So what might that something be? What could end a technological civilization dependably enough to silence an entire galaxy? We do not know, because we have not yet encountered it. But we have been drawing up the list of suspects ever since we first understood what our own technology was capable of. Nuclear weapons, the ability to destroy our own civilization in an afternoon. For nearly 80 years, we have lived with the knowledge that a few thousand detonations would be enough to end the global food supply, collapse every human institution, and possibly render the surface uninhabitable for what remains of our species. The total number of warheads has fallen since the peak of the Cold War, but the number of nations that hold them has grown, and the restraint that has kept them unused has held for less than a single human lifetime. For a civilization that needs to survive for millions of years, 80 years of good luck proves nothing. Engineered pandemics. the capacity to design organisms that do not exist in nature, with a lethality and a transmissibility that no natural pathogen has ever combined. This capacity is advancing faster than our ability to govern it. A single laboratory accident, a single act of malice, could release something that circles the planet before we know it exists. Runaway artificial intelligence, the construction of a mind that does not share our values, our instincts, or our vulnerabilities, and that pursues goals we did not intend and cannot revise. The problem of ensuring that a sufficiently advanced artificial intelligence does what we actually want, rather than what its objective happens to reward, remains unsolved and may be genuinely hard. If every technological civilization eventually builds an intelligence more capable than itself, and if that intelligence is not reliably aligned with its maker's survival, then the outcome could be the same everywhere. The civilization ends, something else continues in its place, or nothing does. But the species that lit the first fire is gone. Climate collapse, the alteration of a planet's atmosphere on a timescale faster than the civilization that caused it can adapt. The burning of stored carbon, the disruption of the cycles that keep a surface habitable. On Earth, we are running this experiment in real time, and we do not know the result. We know only that a technological species can destabilize its own world without ever intending to. These are the candidates, and the list is not complete, but it does not need to be, because they all share a single shape. A species that gains the power to reshape matter and energy on a planetary scale gains, in the very same moment, the power to end itself. The intelligence that lets you build a radio telescope also lets you build a bomb, engineer a plague, wake a mind you cannot control, or change the composition of your own sky. If the power to create always arrives before the wisdom to survive it, and if the first civilization-ending mistake is always final, then every species that reaches our stage soon falls quiet. The lifetime of a technological civilization would be short. A few centuries, perhaps a few millennia, a geological instant, not long enough to cross to the stars, not long enough in most cases even to be heard. That is one fork of the Great Filter, and it is the one where the silence is a warning, where a fossil on Mars is a tragedy, and where we are not the first to stand where we stand, but the latest in a long procession of species that looked up, wondered whether anyone else was out there, and destroyed themselves before they could find out. There is another fork, and on that one, we are safe, not because we are wise, but because we are rare. If the Great Filter lies behind us, then the silence of the universe is not a warning at all. It is a statement about how improbable our own existence really is. The galaxy is quiet because complex, intelligent life is so rare that we may be the only instance of it in the entire Milky Way, and perhaps in the entire observable universe. We are not doomed. We are not typical. We are an accident so unlikely that the cosmos, given 13 billion years and countless worlds to work with, produced it only once. This is the argument of the rare Earth hypothesis, laid out in the year 2000 by the paleontologist Peter Ward and the astronomer Donald Brownlee in a book with a title that states its thesis plainly: Rare Earth, Why Complex Life is Uncommon in the Universe. Ward and Brownlee were colleagues at the University of Washington, one a specialist in the history of mass extinctions, the other in the dust and chemistry of the early solar system. They were not cranks arguing that we are the center of creation. They accepted the Copernican principle for microbes. What they questioned was whether it holds for animals. Their argument begins with a concession. Simple life, they proposed, might be common, perhaps everywhere. The discovery of extremophiles on Earth, organisms that thrive in boiling acid, in rock kilometers below the surface, in the radiation-drenched cooling ponds of nuclear reactors, had convinced many biologists that once life gets a foothold, it is astonishingly tough. It spreads into every crack. It refuses to die. Single-celled life might be a near-automatic consequence of the right chemistry, arising wherever a world offers water, warmth, and time. But complex life, organisms with specialized tissues, large bodies, high energy demands, and eventually nervous systems and brains, is a different matter entirely. Here, the fossil record delivers a sobering fact. For roughly 3 billion years, life on Earth stayed simple. Single cells, then loose colonies of cells, then a few tentative experiments in larger forms, but nothing you could have seen without a microscope. The first Complex, many-celled organisms did not appear until around 600 million years ago, in a period called the Ediacaran. The great flowering of animal body plans, the Cambrian explosion, came around 540 million years ago. For more than 80% of the history of life on this planet, Earth was a world of slime. If an alien survey ship had passed through the solar system at almost any random moment in our biological history, it would have found a living planet with nothing on it more interesting than pond scum, and it would have moved on. Ward and Brownlee's thesis was that the passage from simple life to complex life, and from complex life to intelligent, technological life, is not a single leap. It is a long series of requirements, each of which must be satisfied, and each of which is improbable on its own. Multiply those improbabilities together, and the chance of any given world producing a technological civilization shrinks toward nothing. The great filter on this view is not one wall. It is a corridor of narrow gates, and almost no world makes it down the whole corridor. The requirements begin with the star. Most stars are unsuitable. The largest and brightest burn through their fuel in a few tens of millions of years and then detonate, sterilizing anything nearby before it has a chance to begin. The smallest and most common stars, the red dwarfs, are long-lived but temperamental, prone to violent flares that could strip the atmosphere from any planet close enough to be warm. And planets close enough to be warm around a red dwarf tend to become tidally locked, one face held permanently toward the star in eternal day, the other in eternal night, a configuration that makes a stable climate difficult. The Sun, a steady middle-mass star, sits in a narrow band of stars that are hot enough to warm a world, calm enough not to fry it, and long-lived enough to give evolution the billions of years it needs. Only a minority of stars qualify. Then there is the star's address within the galaxy, too close to the crowded galactic center, and the density of stars means frequent nearby supernovae and bursts of radiation that would repeatedly scour the surface of any planet. Too far out toward the thin edge, and there are simply not enough heavy elements, the carbon, oxygen, iron, and silicon forged in earlier generations of stars, to build a rocky world at all. The Sun orbits in what astronomers call the galactic habitable zone, a ring at a comfortable middle distance where the raw materials are plentiful and the neighborhood is relatively calm. There is a further dimension to that address, and it is a dimension in time as well as space. The early universe may simply have been too violent for complex life to gain a foothold anywhere. In the crowded, chemically raw galaxies of the deep past, catastrophic bursts of radiation were far more frequent than they are today. A gamma-ray burst, the most energetic explosion known, produced when a massive star collapses or when two dead stellar cores merge, releases in a few seconds more energy than the Sun will emit over its entire lifetime. If one were to go off within a few thousand light-years of a living planet, aimed the wrong way, it would strip away the ozone that shields the surface and flood the world with radiation, potentially sterilizing it or triggering a mass extinction. Some scientists have suggested that a gamma-ray burst may have caused one of Earth's own great extinctions, hundreds of millions of years ago. In the early galaxy, such bursts were common enough that large regions may have been repeatedly sterilized, resetting the clock on any life that had begun to develop. Only in the last several billion years, as the galaxy matured and calmed, did stable stretches of space and time open up in which complex life could accumulate the vast ages it needs. On this view, we are not only in a rare place, we are living in a rare epoch, one of the first quiet windows in the history of the galaxy, long enough and calm enough for a mind to form. That would make us not merely uncommon, but early, among the first to arrive at a party that most of the guests have not yet had the chance to reach. The planet itself must clear a long list of conditions. It must sit in the continuously habitable zone, not merely warm enough for liquid water in a single moment, but warm enough to keep water liquid for the billions of years that complex life requires. That band is narrower than it sounds. A world a little too close cooks under a runaway greenhouse. As Venus did, its oceans boiled into a dense, choking sky, and its surface baked hot enough to melt lead. A world a little too far freezes, as Mars did, its thin air unable to hold the warmth. The continuously habitable zone around a star like the Sun is only a fraction of the full habitable zone, and the Earth has managed, remarkably, to stay inside it for 4 billion years its temperature held steady even as the sun itself has slowly brightened. The planet must have plate tectonics, the slow churning of its crust, the recycling of rock down into the interior and back out through volcanoes. This is not a minor detail. Plate tectonics runs a planetary thermostat. It pulls carbon dioxide out of the air and locks it into stone, and it breathes it back out through eruptions. And over long ages, this cycle keeps the climate from tipping into permanent fire or permanent ice. It also builds continents, raises mountains, and creates the endless variety of habitats that drive evolution forward. In our solar system, Earth is the only planet with active plate tectonics. Venus does not have it. Mars does not have it. And we do not know how common it is elsewhere, but the conditions it needs, a world large enough to stay hot inside for billions of years, with enough water to grease the moving plates, may not be easy to meet. The planet must have a large moon. The Earth-Moon pair is a genuine oddity. Our moon is enormous relative to the world it circles, larger in proportion than any other moon around any other planet. The leading explanation is that a body the size of Mars struck the young Earth a glancing blow around 4.5 billion years ago, throwing a ring of debris into orbit that gathered itself into the moon. That is a chance event, dependent on the right impactor arriving at the right angle and the right speed. Without it, Earth would spin without a large companion, and its axial tilt would wander chaotically over millions of years under the gravitational tugging of the other planets, swinging the poles toward the sun and away again, driving climate swings so wild that complex life might never have found its footing. The moon holds our tilt steady. It keeps the seasons within survivable bounds. It is, quietly, one of the reasons you are here. The planet must generate a magnetic field. Earth's field is produced by the churning of molten iron in its outer core, a dynamo driven by heat and rotation, and it wraps the planet in an invisible shield that deflects the solar wind and the constant stream of charged particles blowing outward from the sun. Without that shield, the atmosphere is slowly stripped away into space. This is not hypothetical. It is what happened to Mars, whose core cooled, whose dynamo died, and whose air was peeled off over hundreds of millions of years until the planet became the thin, cold desert we see today. Whether a world can sustain a magnetic dynamo depends on its size, its composition, and its inner heat, factors that vary from planet to planet. And the planet may need a guardian in the outer system, a giant like Jupiter. Jupiter's immense gravity deflects many of the comets and asteroids that would otherwise fall toward the inner planets, acting as a kind of shield for the worlds nearer the sun. It has not stopped everything. The impact that ended the age of the dinosaurs, a rock some 10 kilometers across striking what is now the Gulf of Mexico 66 million years ago, obviously got through, and that catastrophe cleared the stage for the mammals, and eventually for us. But a giant planet in the right place holds the bombardment down to a survivable level. Get the arrangement wrong, put the giant in close to the star, as many of the exoplanet systems we have found seem to have done, with massive worlds whipping around their suns in days, and it disrupts the orbits of any smaller planets, and a stable, temperate world never gets the chance to form. And then, even if every one of these physical conditions is met, there remains the question of contingency, of sheer historical luck. Even on a planet built perfectly for it, the road to intelligence may run through a series of accidents that need not have happened and might never happen again. The evolution of the complex cell, the kind with a nucleus and internal machinery that all animals and plants are built from, appears to have occurred exactly once in Earth's history, when one ancient microbe engulfed another and, instead of digesting it, entered into a partnership that would last 2 billion years. Sexual reproduction, which shuffles genes and accelerates evolution, arose in that same complex lineage. Large brains, language, abstract thought, each was a contingent outcome, shaped by particular pressures and particular disasters, including the ones that removed the competition. If you rewound the tape of Earth's history and let it play again, Warden Brownlee argued, the odds of getting anything like us a second time round are close to zero. The rare Earth hypothesis does not claim to be proven. It is a way of organizing the one example we have, the single living world we can study up close, into a set of hard conditions and asking how often the universe is likely to satisfy them all. But it is the hopeful fork of the great filter. If it is right, then the silence is not doom. It is the echo of extraordinary luck. The galaxy is empty not because civilizations destroy themselves, but because worlds capable of producing and sustaining complex life for billions of years are so scarce that we may be the only one. And that is a lonely thought in its own right. To be the sole intelligence in the galaxy, perhaps in the visible universe, is to carry a weight that no other living thing has ever carried. If we fail, there is no one else. Nothing to inherit the stars. No second attempt. The universe would go dark, not having lost one species among many, but having lost the only mind it ever managed to make. But the rare Earth hypothesis has a problem, and it is the same problem that makes the whole silence so hard to explain away. The galaxy is very, very large. Even if each of Ward and Brownlee's conditions is unlikely, the number of stars is so vast that unlikely things still happen many times over. Conservatively, there are billions of roughly Earth-like planets in the Milky Way. If the chance of complex life arising on such a world is 1 in a million, that still leaves thousands of civilizations. If it is 1 in a billion, it still leaves a handful. But the silence is not partial, it is complete. To explain a complete silence with rarity alone, you have to push the probability not merely low, but almost unimaginably low, so low that it rounds to 0 across the entire observable universe. That is possible, but it means stacking improbability upon improbability until the explanation becomes nearly as hard to believe as the silence it was meant to explain. There is another possibility, one that does not require us to be either cosmically lucky or cosmically doomed, one that leaves the galaxy full of life and full of minds, and still explains why the sky is dark. It is, in some ways, the most frightening idea of all, because it turns our own behavior, our broadcasts, our beacons, our century of shouting into the dark, from a hopeful gesture into a potentially fatal mistake. In 2008, the Chinese science fiction writer Liu Cixin published a novel called The Dark Forest. It was the second book in a trilogy that would become an international phenomenon, translated into more than 20 languages, read by millions, including scientists, technology leaders, and at least one former president of the United States. Liu is not a scientist. He is a novelist, an engineer by training who spent years working at a power plant in the Chinese interior, writing fiction in his spare time. But the idea he articulated in that book has become one of the most seriously discussed answers to the Fermi paradox, argued over not only in book clubs but in scientific journals and at conferences on the search for extraterrestrial intelligence. It has a name now, the Dark Forest Theory. The theory begins from a set of axioms. Liu called them the axioms of cosmic sociology. They are simple enough to state in 2 sentences, and their consequences are what turn the stomach. The first axiom: survival is the primary need of any civilization. This is not a claim about morality, it is a claim about what it takes to persist. A civilization that does not place its own survival above other values will, sooner or later, encounter a situation in which that choice proves fatal, and it will not be there to make any further choices. Over cosmic time, the universe selects for the ones that put survival first, in the same cold way that evolution selects for anything. The second axiom: civilizations grow, and matter and energy are finite. A single star system can support a civilization for a very long time, but not forever, and not without limit. A civilization that keeps expanding will eventually need more room, more energy, more raw material. The galaxy holds a great deal of all three, but not an infinite amount, and every star claimed by one civilization is a star that cannot be claimed by another. The competition is not a matter of temperament. It is written into the arithmetic of growth against a fixed supply. From these 2 axioms, a chain of reasoning unspools, and each link pulls the trap tighter. The first link is the impossibility of trust across interstellar distances. Suppose you detect another civilization around a star 1,000 light-years away. You pick up their transmissions, you study their chemistry and their technology, you learn a great deal about them. But the one thing you cannot learn is what they will become. 1,000 years is a long time for a technological species. Think of how far human capability travelled in the last 1,000 years, and try to imagine the next 1,000. Worse, everything you see is already 1,000 years out of date, because that is how long the light took to reach you, and anything you send back will take another 1,000 years to arrive. You are looking at a photograph of a stranger taken 1,000 years ago, trying to decide whether the person in it now 1,000 years older and armed with 1,000 years of progress, intends you harm, you cannot know. The distances themselves make certainty impossible. The second link is what Liu called the chain of suspicion. You do not know whether the other civilization is hostile. You do not know whether they assume you are hostile. You do not know whether they think you think they are hostile, and the recursion has no flaw. Between two civilizations that cannot communicate quickly, cannot verify intentions, and cannot afford to be wrong even once, the safest assumption is that the other will act to preserve itself at your expense if it ever becomes able to. And because you both reason your way to the same conclusion, you both arrive at the same move. Strike first. Strike before the other one can. In a dark forest, the only way to be safe from a hunter you have glimpsed is to remove the hunter before it removes you. The third link is the one that removes the last comfort. Technological growth is explosive and unpredictable. A civilization that poses no threat today can become an existential threat in what amounts to a cosmic instant. Our own species went from the first powered flight to walking on the moon in 66 years, and from the first programmable computer to machines that outplay any human at the most demanding games in a single lifetime. If those rates are anywhere near typical, then a civilization you judge to be harmless might, by the time your judgment even reaches them, have leapt far beyond you. So you cannot afford to let a weaker neighbor live and grow, because weakness is temporary and the growth is exponential. The logic of the preemptive strike is not a logic of cruelty. It is a logic of survival in a place where hesitation can be fatal and where you get no second chance to correct a misjudgment. The conclusion Liu drew is stark and total. The universe is a dark forest. Every civilization is a hunter, moving silently among the trees, gun in hand. To reveal your position, to make a light, to make a sound, is to die. So everyone who has learned the rules stays hidden, everyone stays quiet. The silence of the cosmos is not a mystery to be solved. It is a strategy being followed by everyone, all at once. The Dark Forest is a work of fiction, but it is fiction that has been taken seriously because it fills a gap that the other explanations leave open. Most proposed solutions to the paradox explain why civilizations might be rare or why they might die young. The Dark Forest explains why they might be abundant and long-lived and still completely invisible, not because they cannot speak, but because they have all decided, independently, that speaking is suicide, and here on Earth, we have spent the last century doing the exact opposite of staying quiet. The debate over deliberate messaging to the stars, the practice of aiming a powerful transmitter at another star and announcing ourselves on purpose, has become one of the sharpest disagreements in the field. For most of the history of the search, the strategy was purely passive. We listened. We pointed radio telescopes at nearby stars and swept the sky for narrow signals that nature could not make. There is no risk in listening. A received signal cannot harm you, and the sender never knows you heard. You stay invisible. But some scientists argued that listening is not enough. If everyone only ever listens, no one ever makes contact. Someone has to speak. In 1974, Frank Drake and Carl Sagan used the newly upgraded Arecibo radio telescope in Puerto Rico to broadcast a message toward a distant cluster of stars. A simple pattern of on and off pulses that, arranged into a grid, sketched a human figure, the chemistry of our genetic material, the layout of the solar system, and the telescope itself. It was aimed at a globular cluster tens of thousands of light years away, so far that the message will not arrive for longer than our species has so far existed, and by the time it does, the cluster will have drifted from the spot the beam is aimed at. It was a gesture, not a serious attempt at conversation, but the principle had been crossed. We had spoken. Other transmissions followed. A Russian astronomer, Alexander Zaitsev, used a powerful radar dish in Crimea to beam several messages toward nearby sun-like stars, arguing that humanity had a moral duty to announce itself, to add its voice to the galaxy rather than crouch in fearful silence. He believed the universe was more likely benign than hostile, and that the danger of staying silent forever outweighed the danger of being heard. Many of his colleagues were appalled. The astrophysicist and novelist David Brin became one of the most persistent critics of deliberate messaging, and his objection was not that aliens are certainly dangerous, but that no small group of enthusiasts has the right to make that gamble on behalf of everyone. The risk, whatever its size, falls on the entire species, on every nation, on every generation not yet born. A decision that could in principle endanger all of humanity should not be taken quietly by a handful of scientists with access to a transmitter. Brin has called for open international discussion before any further deliberate broadcasts. No such agreement exists. The transmitters remain. Anyone with a powerful enough dish could, in principle, decide to shout. When Stephen Hawking was asked about the wisdom of contacting extraterrestrials in a documentary series made in 2010, his answer was blunt. Meeting a more advanced civilization, he suggested, might go for us roughly the way the arrival of Europeans went for the native peoples of the Americas, and that, he noted, did not turn out well for them. Hawking was not claiming that aliens are inherently cruel. He was making a point about power. When a far more advanced society meets a far less advanced one, the encounter has historically been ruinous for the weaker party, and not always through deliberate malice. Sometimes it is disease, sometimes it is displacement, sometimes it is simply the shattering of a way of life that cannot absorb the shock fast enough. Any civilization that reached Earth from another star would be, at the very least, centuries ahead of us, and more likely thousands or millions of years ahead. The gap would not be a gap, it would be an abyss. The dark forest theory takes that warning and makes it universal. It says that every civilization which survives long enough eventually learns the same lesson. The forest is full of hunters, and the only way to live is to become one and then vanish. Make no sound, send no signal, erase every trace of yourself from the view of anyone who might be watching. From inside that logic, the human strategy of the last 100 years looks not merely naive but reckless. We have been leaking radio into space since the early 20th century, a swelling bubble of television and radar and chatter, now more than 200 light-years across. It is faint, and it thins with distance, but a civilization with sensitive enough instruments could in principle notice it, could see a star that suddenly, in the middle of the 20th century, began to hum with structured, artificial signals, and could conclude that something on the third planet had woken up. The dark forest theory says that if anyone out there has heard us, they are not sending a reply, they are deciding what to do. And the logic of the forest allows them only one rational choice. This is a terrifying picture. It turns the silence of the universe from a sign of emptiness into a sign of concealed danger. The quiet is not the quiet of an empty room. It is the quiet of a room full of people holding their breath. It is worth understanding why the logic feels so airtight to those who take it seriously, and it comes down to an asymmetry between how easy it is to destroy and how hard it is to defend. Across interstellar distances, an attack does not need to be clever. It needs only to be fast and heavy. A single object, a rock, a slug of metal, accelerated to a large fraction of the speed of light, and aimed at a star system, carries an energy that no planetary defense could absorb, and it arrives with almost no warning, because it travels only slightly slower than the light that would announce it. You would see the flash of its approach at nearly the same instant it struck. There is no interception, no negotiation, no time to react, and crucially, the attacker never has to reveal itself. The projectile can be launched from the dark, from an unknown origin, and by the time it lands, the sender may be 1,000 years and 1,000 light-years away, untraceable and unaccountable. Set that against the situation of the target. To be safe, you would have to defend against an attack that gives no warning, from a direction you cannot predict, launched by an enemy you cannot locate, at a moment you cannot foresee. It cannot be done. The only defense is to never be seen in the first place. And this is what closes the trap. In a universe where being noticed can get you destroyed at any moment, by anyone, without warning, the rational move for any civilization that understands the game is to make absolutely certain it is never noticed, to go dark, and to consider going dark not a temporary tactic, but a permanent condition of survival. The silence, on this reading, is not the silence of a graveyard or of an empty room. It is the disciplined, deliberate silence of everyone who has already worked out the rules and has no intention of being the one who breaks them. There is a grim corollary that follows for us. If the dark forest is real, then the correct response to detecting another civilization is not to say hello. It is to say nothing and to think very hard about what to do. and the same is true of anyone who detects us. We have spent a century assuming that making contact would be a triumph, the beginning of a conversation. The Dark Forest says that making contact might be the last thing a civilization ever does. Whether that is true, no one knows. But it is sobering that our instinct, as a young and hopeful species, has been to shout as loudly as we can into a dark we do not understand, on the assumption that anyone who hears us will be glad we called. But the Dark Forest has a weakness, and it is worth seeing clearly. It assumes that every civilization reasons its way to the same conclusion from the same premises, that the preemptive strike is not merely one possible response, but the only rational one. Yet human history, our single sample of first contact between unequal powers, is not uniformly a story of extermination. Many such encounters were catastrophic. Some were not. There was trade, there were alliances, there were centuries of uneasy coexistence. The conclusion that the only safe move is to destroy every civilization you glimpse is not a theorem. It is a choice, and not every mind need make it. And the theory works only if the silence is universal. If even one advanced civilization rejects the logic, if even one decides that the risk of reaching out is worth taking, or that cooperation beats extermination, then the forest is broken. That one would make contact, form ties, build a network, and the silence would end. The fact that the silence has not ended suggests either that every civilization without exception has embraced the hunter's logic, which is a very strong assumption to make about every mind that has ever existed, or that something else is keeping the sky quiet, something that does not require everyone, everywhere, to be equally afraid. There is another possibility, a gentler one. What if the silence is not a strategy of fear, but a policy of care? What if the galaxy is quiet not because we are prey, but because we are being protected? The year was 1973. The Apollo program had just ended. The last human footprints had been pressed into the lunar dust, and the search for extraterrestrial intelligence was moving from the fringe toward the scientific mainstream. A radio astronomer named John Ball, working at the Harvard College Observatory, published a short paper in the journal Icarus. The paper was called The Zoo Hypothesis. Its argument was elegant and disquieting in equal measure. Ball began with the same observation Fermi had made 23 years earlier. The galaxy should be full of intelligent life, and we should see evidence of it. We do not. The usual explanations, that interstellar travel is impossible, that civilizations destroy themselves, that we are simply alone, seem to Ball either physically doubtful or statistically strained. So he proposed a different kind of explanation, one that did not require us to be unique, one that did not require physics to be a wall, one that did not require every other civilization to be dead. What if we are not alone, and we are not ignored, and we are not in danger? What if we are being deliberately left alone? The zoo hypothesis states simply that the extraterrestrials know we are here. They have the ability to contact us, or to visit us, or to make their presence unmistakable. They choose not to. And the reason for that choice, Ball suggested, is much the same as the reason a zookeeper does not climb into the enclosure and introduce himself to the animals. Contact would disrupt the natural development of the thing being observed. It would contaminate the very phenomenon the observers came to study. The most respectful course, the one that honors the autonomy and the natural path of a younger civilization, is to watch and to stay out of sight. Ball was not the first to imagine this. The idea of a rule forbidding interference with less advanced cultures had been a staple of science fiction for years, most famously as the prime directive of a certain television starship, which had entered the popular imagination only a few years before Ball wrote. But Ball was among the first to frame it not as fiction but as a testable scientific hypothesis, a genuine candidate answer to Fermi's question. The zoo hypothesis does not require every extraterrestrial civilization to be gentle. It requires only that one of them is powerful enough to set the rules and enforce them. If a single advanced civilization decided, long ago, that emerging intelligences should be left undisturbed to grow, and if it had the reach to prevent others from meddling, then the silence is explained. We would be living inside a preserve, a nature reserve on the scale of a galaxy, its boundaries invisible, its wardens undetectable, its policy absolute. We would look up at a sky that seemed empty precisely because someone had decided it should look that way to us. This idea has a strange effect on the feeling of the silence. The The dark forest makes every quiet star a threat, a hunter holding its breath. The zoo hypothesis makes the same silence tender. It recasts the emptiness not as danger, but as courtesy. The universe is not ignoring us. It is giving us room. There is a mathematical elegance to the way a single civilization could impose this quiet on everyone else. It does not require a vast empire policing every star. It requires only that the first civilization to reach true galactic power got there early and decided the rules. In a galaxy where expansion is as fast as the physics allows, the first species to spread would not meet a crowd of equals. It would meet an empty galaxy, and it would fill it, and everything that arose afterward would arise inside a territory already claimed and already governed. A latecomer like us would not be negotiating with our peers. We would be growing up inside a house built long before we were born, whose owners we have never seen, whose rules we have never been told, and whose presence we infer only from the strange, total quiet. 10. That reframes a question we tend to ask backwards. We ask why, out of all the civilizations that might exist, none of them has contacted us. But if the galaxy has a single dominant power that reached maturity billions of years ago, then there is only one relevant decision, made once, long before humanity existed, the decision to leave developing worlds alone. Every other civilization, if there are others, would live under that same decision, in the same silence, for the same reason. The uniformity that sinks the dark forest and the zoo hypothesis both, the improbable idea that thousands of independent civilizations all behave the same way, dissolves if the behavior was set once, at the beginning, by whoever got there first. Ball himself was careful to note that his hypothesis, like most answers to the paradox, is very hard to test. That is its greatest weakness as science. A theory that predicts we will see nothing and explains any silence we observe risks explaining too much. If no possible observation could ever contradict it, then it is not doing the work science requires. Ball acknowledged this. He offered the zoo hypothesis not as a proven fact, but as a possibility that could not be ruled out. A reminder that an empty-looking sky is consistent with more than one story, and that absence of contact is not the same as absence of neighbours. The most he claimed was that if the wardens exist and are competent, we would experience exactly the universe we do experience, full of habitable worlds, silent in every direction, with no way to tell whether we are truly alone or merely being given our privacy. Consider what it would mean if it were true. Somewhere, perhaps not far in cosmic terms, there are minds that have watched the whole of human history unfold. They saw the first cities rise between the rivers of Mesopotamia. They watched the pyramids go up, the empires rise and fall, the long, slow bloom of the sciences, the sudden industrial darkening of the skies. They watched the 20th century with its wars and its bombs, and its first fragile steps off the planet. They saw the footprints go into the lunar dust. They are watching this moment now, as these words are spoken and as you hear them. And across all of it, they have chosen not to intervene. The reasons for such restraint, if it exists, would have to be strong. Ball and others who developed the idea have offered several. The most straightforward is scientific. A civilization emerging on its own, from stone tools to starships, is a rare and precious thing to study, and contact would ruin the experiment. It would be like a naturalist climbing into a nest to greet the birds. After that, the birds would never behave naturally again. If complex intelligent life is genuinely uncommon, then each instance of it is data too valuable to spoil. A second reason is ethical. A civilization vastly older than ours might hold moral commitments we cannot yet imagine. Chief among them a deep respect for the self-determination of younger minds. They might look at our wars and our famines and our chaos and understand them as necessary stages in a process that cannot be short-circuited without doing harm. To hand us their technology before we are ready would be to make us dependent. To solve our problems for us would be to rob us of the chance to learn how. The kindest course, in that view, is to let a species grow up at its own pace, however painful it is to watch. A third reason is colder. The civilization keeping its distance might not be doing it for our benefit at all, but for its own. A young technological species is volatile and unpredictable, and the safest way to handle something volatile is to keep it contained, observe it, and wait to see whether it stabilizes or destroys itself. In this darker reading, The zoo is not a sanctuary. It is a quarantine. The silence is not a kindness." And quote, "It is a cordon drawn around something that might be dangerous. Whatever the motive, the zoo hypothesis makes a clean prediction. If we are being watched by minds that do not wish to be seen, then we should not be able to see them, and we cannot." That is not a flaw in the idea. It is a requirement of it. A civilization able to cross between the stars and enforce a policy of non-interference across a whole galaxy would command technologies so far beyond ours that hiding from us would cost them no effort at all. Their communications might run on channels we have not discovered, beams of neutrinos, ripples in gravity, methods we have not yet dreamed of. Their vehicles, if they use vehicles, would be cloaked or shrunk or disguised as ordinary rock. A probe of theirs, sitting quietly somewhere in our own solar system, could easily escape every instrument we have ever built. That last idea has a name of its own. In 1960, the astronomer Ronald Bracewell proposed that an advanced civilization, rather than blasting radio across the galaxy, might simply place a small probe in orbit around a promising star and have it wait, watching, listening, and ready to announce itself only when the locals reached a certain level of sophistication. A Bracewell probe would be a kind of patient messenger, an answering machine parked in the dark, holding its reply until we were ready to receive it. If such a thing sits somewhere out among the moons and asteroids, we have not found it, but we have barely begun to look. The solar system is enormous, and a quiet object in a wide, cold orbit could stay hidden from us indefinitely. The unsettling part of the zoo hypothesis is not the being watched, it is the terms of the watching. The observers might decide, at any moment, that the observation period is over, that we have crossed some threshold that ends the quarantine, the first nuclear detonation perhaps, the birth of an artificial mind, a colony planted on another world. Any of these might be the line that, once crossed, changes everything about how we are treated. We would not know the line was there until we had stepped over it. There is a broader version of this idea that has circulated among researchers for decades. Sometimes, it is called the idea of a galactic club. In this picture, the galaxy is not empty but populated, an established community of civilizations that have survived their own technological adolescence and that keep their distance from newcomers by agreement. A young species is not contacted until it reaches a certain maturity, because premature contact does harm, as our own history of collisions between unequal cultures grimly demonstrates. So the club waits. It watches, it leaves us alone, and it admits new members only once they have proven they can be trusted not to destroy themselves. When might that moment come? Some who have thought about the zoo hypothesis suggest the threshold is the point at which a civilization stops being a danger to itself, the moment it learns to govern itself across a whole planet without war, the moment it stabilizes its climate, the moment it demonstrates that it can hold the powers it has built without turning them on itself, which is to say, the moment it proves that its own value of L is going to be large, the moment it passes the great filter under its own power. There is something almost devotional in that framing. It turns the Fermi paradox from a puzzle into a rite of passage. The silence is not a void, it is a waiting room. The universe is holding its greeting until we have grown up enough to survive hearing it. But the zoo hypothesis carries the same flaw as the dark forest, and it is fatal to both in the same way. Each of them requires everyone to comply. The dark forest needs every civilization to be a hunter or a corpse. The zoo needs every civilization to honor the quarantine or to be prevented from breaking it. And in either case, it only takes one civilization that decides to answer, one that decides to reach into the enclosure, one that simply does not agree with the rule. If the galaxy has produced thousands of civilizations across billions of years, the odds that every single one of them abides by the same code or is held in check by the same power are not good. A single exception unravels the whole arrangement, and the silence should long ago have been broken by somebody, yet it holds. Unless, of course, the thing enforcing the silence is not a policy at all, and not a fear, but a simple, unfeeling fact about the shape of space and time. Unless contact is rare, not because anyone chooses to make it rare, but because the universe is built in such a way that two voices almost never manage to overlap. Unless the silence has nothing to do with anyone's intentions, and everything to do with the crushing distances between the stars and the brief flicker of any civilization's life, that is a different silence. Not the silence of hunters, and not the silence of zookeepers, the silence of light years and of time. There is a way of looking at the Fermi paradox that needs no filters, no hunters, no zookeepers, no vanishingly rare worlds. It needs only that we take the distances between the stars seriously, not as numbers on a page, but as what they actually are. Gulfs so wide that even light, the fastest thing there is, takes years to cross from one star to the next. And it needs us to remember that civilizations are not only places, they are also moments. They begin, they last for some span of time, they end. The real question is not only whether two civilizations are near enough in space to touch, it is whether they are near enough in time to overlap at all. The Polish writer Stanislaw Lem, one of the great and underread minds of the 20th century, thought about this problem with more honesty than almost anyone. Lem lived through the Nazi occupation of his homeland, through the Stalinist years, through the long grey decades of the Cold War, and he wrote about contact with the alien not as an adventure, but as a philosophical trap, a problem that might have no solution, and whose deepest lesson might be about the limits of the human mind, rather than about the aliens at all. In his novel, His Master's Voice, published in 1968, and across his essays on the Great Silence, he developed an idea that has come to be called the window of contact. The idea is plain. A technological civilization does not shout into space forever. It passes through a phase, a surprisingly short phase, during which it leaks or beams detectable signals into the dark. Before that phase, it is silent. After that phase, it is silent again. The window is open for perhaps a few centuries. Then it closes. Look at what has already happened here. For the first 4.5 billion years of Earth's existence, the planet sent no artificial signal into space at all. None. An alien astronomer pointing a receiver at the Earth at any moment across those aeons would have heard nothing but the hiss of a natural world. Then, a little over a century ago, we began to make radio. At first it was faint and scattered, the first sparks of Hertz and Marconi, the first wireless telegraphs, the first broadcasts. By the middle of the 20th century, the planet had grown loud with commercial radio, television, and above all military radar, some of it powerful enough to cross interstellar distances. For a few decades, Earth blazed in the radio spectrum, but that loud phase is already fading. We are abandoning high-power broadcasts that spray signal in every direction. Television and radio move increasingly through buried cable and fiber and tight satellite links that spill almost nothing into space. Mobile networks run on low power and shrinking cells. Old radar systems are being retired in favor of quieter, more efficient designs. The radio brightness of the Earth, which peaked somewhere in the late 20th century, is now in decline. In another century or two, it may sink back toward invisibility, not because we have fallen silent as a civilization, but because we have simply learned to speak more efficiently. Lem's insight was that this is probably true of everyone. Every technological civilization broadcasts loudly for a while, then goes quiet, not out of fear, and not because it has died, but because crude, powerful, omnidirectional radio is a beginner's technology, something a civilization does in its infancy and then outgrows. The galaxy could be full of civilizations exactly like us, or a little ahead, or a little behind, and we would never know, because their windows of loudness are too narrow to catch. The chance that two such windows happen to overlap, in time and in space, across gulfs of hundreds or thousands of light years, is vanishingly small. This is not a frightening idea. It is, in its own way, almost consoling. The silence of the universe is not the silence of death. It is the silence of mistimed signals. The galaxy is full of voices, but they are scattered across millions of years, each one calling out for a brief moment and then falling quiet before anyone within earshot happens to be listening. The signals are real. They are out there right now, rushing through space at the speed of light, washing over worlds that are still molten, passing through systems that will not bear life for another billion years. They go unheard, not because no one is speaking, but because the listeners either have not yet been born or crumbled to dust long ago. Put a number to it, and the loneliness comes into focus. Suppose the galaxy has produced 1,000 technological civilizations across its whole history, a modest number, given everything we said at the start. Suppose each one is detectable for 500 years before it goes quiet. Then the total time during which any civilization at all is broadcasting, added up across the entire history of the galaxy, is 500,000 years. That sounds enormous. It is longer than our species has existed, but it is only about 1 part in 20,000 of the galaxy's age. Pick a random moment in that history, point your telescope at a random star, and the chance of catching a civilization mid-broadcast is around 1 in 20,000, and that is if you already knew which star to aim at. The galaxy holds hundreds of billions of stars. The overwhelming majority will never host a civilization at all. The rare ones that do will host it for a heartbeat. Finding one that happens to be transmitting in the same slice of time that you happen to be listening is not merely hard, it is close to impossible. And this assumes the civilizations are like us, using radio and then moving on. What if the step after radio is not some technology we can already imagine, like tight-beamed light, but something we cannot imagine at all? A way of communicating that rides on physics we have not discovered, carried by particles we cannot detect. A civilization 1,000,000 years past radio might be as invisible to our instruments as a television broadcast is to a bacterium, not because it is hiding, because we do not have the organs to perceive it. Carl Sagan liked to point out that if aliens had visited Earth during the age of the dinosaurs, 100 million years ago, they would have found a rich, living world with no trace of intelligence anywhere on it. They would have catalogued the giant reptiles, noted a promising but unremarkable planet, and moved on, leaving perhaps a single line in some vast survey. They would have had no reason ever to return, and by the time intelligence finally did stir here, tens of millions of years after the last of those reptiles died, the visitors would be long gone, their civilization perhaps ended, their home star perhaps burned out, their brief record of Earth buried under 100 million years of cosmic time. The mismatch cuts the other way too. Even if a civilization is listening right now, and even if its window happens to overlap with ours, it still has to be close enough for our signals to have reached it. Our radio bubble is only about 130 light years across. That is a tiny neighborhood. A few thousand stars, a rounding error in a galaxy 100,000 light years wide. A civilization on the far side of the Milky Way that is listening at this very moment will not hear our first broadcasts for another 50,000 years. And 50,000 years from now, our window may be shut. We may have moved on to quieter technologies, we may have destroyed ourselves, we may have become something we cannot now imagine. The message that finally arrives at their receivers would be a ghost, the recorded voice of a civilization that no longer exists, sent by a species that can no longer answer. Here is a way to feel it. Imagine you are one of those first radio waves launched from a transmitter on Earth in the 1930s, racing outward at the speed of light. You have been travelling for the better part of a century. You have already swept past the nearest stars, past Alpha Centauri, past the small red suns of our immediate neighbourhood, and not one of them held anyone tuned to your frequency at the instant you passed. Ahead of you lie tens of thousands of years of empty distance before you even reach the far reaches of this one galaxy, thinning all the while, growing fainter, until eventually you are weaker than the background hiss of the universe itself, and no instrument that could ever be built would be able to pull you back out of the noise. You are a message with no guaranteed recipient, thrown into a dark so wide that the odds of anyone catching you are almost none. This is not a tragedy of malice. It is a tragedy of scale. It is worth being honest about how weak our own signals truly are. The idea that Earth is broadcasting its presence to the galaxy is, for the most part, a comforting myth. The everyday radio and television leakage we imagine spreading outward becomes, within a few light years, so faint that detecting it would require a receiving dish larger than anything we could plausibly build, aimed at exactly the right star, at exactly the right time, sifting our chatter out of the natural roar of the sun and the galaxy behind it. Only our most powerful, deliberately focused transmissions, planetary radar, the occasional intentional message, have any real chance of being noticed across interstellar distances, and those are brief, narrow, and rare. So even the sphere of noise we picture expanding around us is thinner and quieter than the image suggests. If a civilization exactly as advanced as ours sat around a nearby star, listening with instruments exactly like ours, it would almost certainly hear nothing from us at all. We are not, in truth, shouting into the dark. We are whispering, and mostly to ourselves. The silence we hear from others may be, in large part, the same kind of silence we ourselves are producing. Not an absence of anyone, but a signal too faint, too fleeting, and too easily lost to ever be caught. This is the loneliness of time, and it is a deeper loneliness than the one we feel imagining ourselves alone in space. Space is lonely in a way we can picture: empty distances, silent stars, the void between the galaxies. But time is lonelier because to be separated from another mind by 1,000,000 years is a more complete isolation than to be separated by 1,000,000 light years. A distance in space can, in principle, be crossed, if you are patient enough. A distance in time cannot be crossed at all, in either direction, by anyone, ever. Lem understood this. He wrote of civilizations as brief flames, each one convinced it stood at the center of things, each one straining to hear voices that had either not yet begun to speak or had already fallen forever silent. The silence, in this reading, is not a paradox at all. It is the ordinary condition of a universe that is not a network but a scattering, countless isolated moments, each sealed off from all the others by the one-way current of time. And there is one more possibility, which makes even the loneliness of time look simple. What if the universe is full of life and full of minds, and we cannot see them, not because they are too far away in space or time, but because we do not recognize them when we look straight at them? Everything we search for is a reflection of the only life we know. We look for liquid water because we are made of it. We look for oxygen because we breathe it. We look for worlds at Earth's temperature, with Earth's chemistry, because Earth is the single example we have. But what if life can take forms we have not thought to look for? What if it can be built on silicon rather than carbon, running its chemistry at temperatures that would boil or freeze our own? What if it thrives in the frigid methane lakes of Titan, where water is a mineral as hard as rock, and rivers of liquid gas run cold under a golden haze? What if it drifts in the clouds of a giant planet, feeding on lightning and chemistry, never touching a surface at all? What if there are things living slow and vast inside the crusts of dead worlds, or fast and strange in the plasma of a star's outer atmosphere, on timescales so different from ours that a thought of theirs might take 1,000 of our years, or 1,000,000th of a second? We would not call any of it life. We might not even notice it. These ideas sound like fiction, and some of them are, but the underlying point is solid. We do not know what life is in general. We know what it is here. Our entire search for it elsewhere is, unavoidably, a search for ourselves, for the chemistry we run on, the signals we send, the worlds that resemble our own. If life can be radically otherwise, if minds can arise in media we have never considered, on physics we have never touched, then we could be staring straight at a living, thinking cosmos and seeing nothing but dead matter. There is a version of this that reaches even further. Some researchers have wondered whether the most advanced civilizations do not expand outward at all, but inward, shrinking their activity into ever smaller, denser, faster forms of computation, retreating from the vast cold spaces we search into a private inner universe we have no way to perceive. Others have proposed, more strangely still, that a truly ancient civilization might simply be waiting, deliberately dormant, sleeping through the present hot era of the cosmos, because information can be processed far more efficiently when the universe is colder, and the universe will grow colder for trillions of years to come. A civilization following that strategy would have gathered its resources, gone quiet, and set an alarm for the deep future, leaving the galaxy to look, to any young species stumbling out into it now, exactly as empty as it looks to us. On any of these pictures, the silence is not absence. It is a form of presence we are not equipped to read. The silence, in this final turn, stops being a fact about the universe and becomes a fact about us, about the limits of our imagination, about the narrowness of our instruments. We hear nothing because we have not yet learned how to listen for the kinds of voice that are speaking, and this is, in a way, the most hopeful possibility of them all. It means the universe is not a graveyard, and not a dark forest, but a crowded room in which we are the ones who have not yet learnt the language. The silence is not a verdict. It is a measure of how much we still do not understand. And that is where we must leave the question. Not with an answer, but with the specific weight of the unanswered. The Fermi paradox, after more than 70 years of hard thinking, has not been resolved. It has been deepened. Every proposed solution reflects something about the people who proposed it, their fears, their hopes, their assumptions about what a mind is and what it wants. The rare world thinkers see a universe of extraordinary luck. The great filter thinkers see a trial still ahead. The dark forest thinkers see hunters in the trees. The zookeepers see a preserve. Lem saw the loneliness of mistimed flames. Each of them is looking into the same darkness and describing what they brought with them. The silence is a mirror, and we have been staring into it for a long time. But one thing every serious attempt at the paradox shares, and it is not in dispute. The silence is real, and it will not last forever. Either we will break it, or we will join it. I want to return now to the shore where we began. The ocean stretching out in every direction, black and silent, not one light on the water. You have been standing there a long time, long enough to understand the size of the ocean, long enough to have turned over, one by one, all the reasons the lights might be missing. Perhaps the islands are barren, and only ours ever caught fire. Perhaps the fires were lit and went out every time, and something waits to put out ours too. Perhaps the fires are there but hidden, banked low by things that have learned that any light draws hunters. Perhaps they are hidden out of kindness, and someone is waiting for us to be ready. Perhaps the fires are simply scattered too far across time to ever see one another. You have held all of these tonight, and set none of them down, because no one can yet say which is true. But you know something now that you did not know when you arrived. This is not a question you get to consider from a safe distance. You are standing on one of the islands, and the island has just lit its fire. We have been broadcasting for a century. Our signals are spreading outward at the speed of light, a bubble of noise now more than 200 light-years wide, and we do not know who, if anyone, is inside it. We are approaching the moment when the great filter, if it lies ahead of us, would begin to make itself felt. The powers that could end us, the weapons, the engineered plagues, the minds we are building without fully understanding them, the slow alteration of our own sky, are the very same powers that could carry us to other worlds and make us permanent. Each of them is a door that opens both ways. Each of them is a test whose result we will only be able to read afterwards, and if we fail it, there will be no afterwards in which to read it. That is the part of the Fermi paradox that stays with people in the dark. Not the question of whether anyone else is out there, the question of whether anyone else will be, whether the sky is quiet because civilizations are rare or because they are brief, whether we are the first or merely the latest. I told you at the beginning that a fossilized bacterium on Mars would be the worst news our species has ever received, and I hope the shape of that claim is clear now. A second, independent origin of life in our own solar system would mean that life is easy, that the beginning is not the hard step, and that the hard step lies somewhere ahead of us, waiting. The silence would stop being a puzzle and become a verdict on the lifespan of technological civilizations, a verdict that reads, "They do not last." But we have not found that bacterium, not yet. The Martian soil is still ambiguous. The methane still has no settled explanation. The samples Perseverance has sealed in their tubes are still sitting on the surface of another planet, uncollected, their secret intact. The question is open, and while it is open, the other possibility remains alive, that life is genuinely rare, that the origin of life is the hard step, that the filter is behind us and we are already through it. If that is so, then the silence is not a warning, it is an inheritance. The galaxy is empty because no one else has ever come this far, and it is ours to fill or to waste. That is a heavy thing to carry, heavier in some ways than the fear of extinction. To be the first is to know that everything that comes next depends on us, and that no one is coming to help. There is no older, wiser civilization waiting to teach us how to hold our own weapons, or settle our own quarrels, or cool our own sky. There is no club preparing to admit us. There is no one out there with the answer. There is only us, and the silence, and a very long night that may or may not have a morning. The universe is 13.8 billion years old, and it has trillions of years still to run. The stars now burning will burn out, and new ones will form from the ash, and in time even those will fade, and the sky will go dark. But between now and then there is time. Time enough for life to reach out from this one small planet toward every corner of the galaxy. Time enough to become the voice that some far younger species, standing on some far shore, finally catches the fire on the horizon that tells them they were never alone. The ocean is still in front of you, still vast, still dark, still quiet. Whether it stays quiet is the one part of the question that has not yet been decided, and the deciding of it has been left, strangely, improbably, to us. Good night.